Test 1, 2, test. Good morning, everyone. Sorry, we're just getting the last AV set up. Please bear with us for a few minutes, but we'll get started soon.
Alex, Daniel's promoted.
Can you say that again? Sorry.
Daniel is promoted to panelist.
Got it. Thanks. Levon, can you bring up Alex Rudkevich's slides? This is number 41. Check 1, 2, check 1, 2. Okay. This should we got mute this. Okay. Test 1, 2. Oh, it's still coming out here. Check 1, 2, check 1, 2. Oh my God. Levon, can you mute this computer at the podium here? Okay. Oh, speaker, there you go. Oh, check 1, 2, check 1, 2. Okay, that's perfect. Thank you. All right. Close call. Okay. All right, good morning, everyone. Thank you for your patience as we get set up here. We're ready to go ahead and get started. Session WB1. We're going to welcome our first speaker, who is Dr. Aleksandr Rudkevich. He's the president of Newton Energy Group. He'll be speaking on Stochastic Nodal Adequacy Pricing Platform, or SNAP. Dr. Rudkevich, please.
Thank you. So how do I control the?
The slides will be advanced for you.
Oh, okay. But would I once I will see them, right?
Can you, Levon, can you please display Dr. Rudkevich's slides again?
Yeah.
No, it's 1 second.
Okay, great. Thanks.
What's that window for you? Something away.
Okay. Okay, thanks. So we can get started with this presentation. This is Stochastic Nodal Adequacy Pricing Platform, or spot pricing of reliability, in some sort of reference to Richard Tavers's book, Spot Pricing of Electricity. Next slide, please. Can you put the next slide?
Levon, can you hear us? Can you advance the slide, please?
I can hear him trying to figure out what's going on here.
Okay, thank you.
We're having tech.
Okay,
Great.
so the project is funded by ARPA-E, and this is just the summary page on the ARPA-E website related to that project. So we are on the third and the final year of the project. We're almost done. So we discussed today the kind of the ideas and the summary of the results, and also the next presentation by Selin Yanikara. She will go into more details on some sort of computational aspects of the projects and how it's actually done. Next slide, please. So the team members are the company TCR, Newton Energy Group, Polaris, IBM Weather Company, and MISA as a participating partner in this project. Next slide, please. So the idea is, what we want to achieve is to develop a system that would be evaluating the adequacy of the large electrical systems, such as the size of MISA or any other RTO. We'll be evaluating it every day for the next day or several days. We'll do it nodally. We'll identify extreme inadequacy events probabilistically in that system, and compute the value of adequacy for every element of the system, every power plant, every demand resource, or every transmission line. It would do it nodally, truly nodally. And with that, it would also provide the economic value of adequacy and measure monetarily the contribution of every asset to providing adequacy. So what's the value of power plant providing adequacy in that given location, and now what's the value of a transmission line? What's the value of the demand resource? What's the value of any other technology? That's the idea. So the next slide, please. So if we think about traditional resource adequacy tools, and we say, can we actually trust these tools in predicting and measuring the extreme events? The answer is most likely no, we can't. Because to the best what we know, these tools are rely on, and for a good reason. We have explanation why is so. they rely on stylized power system models that do not properly represent the physics of the system. Like we very often in these models, transmission networks are just ignored. They rely on sort of pipes and bubble representation. They do not represent operational limitations of the system, and also do not represent the impact of uncertainty. So when the decisions are made with no perfect knowledge of what's going to happen. And when we are looking at sort of when the events occur, how the system responds to that. So effectively, if we think about this, the models that we use, they're kind of good on average, but we're looking at the system under the extreme conditions, which is typically not average. So you can't really rely on this type of tools with the system. So we really need something much more high fidelity, like security constraint unit commitment type tools, and we need to run them in Monte Carlo fashion. So that's the challenge, how you do it. So that was the kind of the impetus for this project. So to develop the approach and also integrate the weather uncertainty because it's critical. Next slide, please. Now, this is the formula, kind of the key formula behind this whole logic, and which is relatively simple. What we see here is the expected marginal unserved energy, which is perturbed at any specific location at any specific point in time, multiplied by the value of lost load. That's essentially the value of reliability at any point in time, at any location in space. Right, so it's like, what would it cost me to deliver, to serve an extra unit of energy at a time of scarcity? That's the question, and that cost depends on where you try to serve this load. So everything that happens is ultimately kind of a computational and logical implementation of this formula. Next slide, please. So our probabilistic world is effectively the sort of the product of the uncertainty in the weather and uncertainty in the system behavior, right? So in terms of uncertainty in the weather, we have uncertain loads, we have uncertain wind, uncertain solar, which are all weather driven. Also, the transmission line ratings are weather driven, and forced outage rates are also weather driven. So we can have a kind of representation of the probabilistic weather forecast translated into all these components. And then it should be sort of played over the random outages of the assets, which could be the generation outage and transmission outages. So looking at these combinations of things, we want to process it, analyze using the kind of production costing tool for every possible scenario. Run the statistical analysis through Monte Carlo and then post-process the results. Next slide, please. So the first component is the weather. Now that comes from, the team's contribution here is based on what is done by the weather company at IBM. So next slide, please. So essentially, they have their technology which they use. We all rely on the weather forecast that they produce. Like, I have an app on my phone. And essentially what they do, they combine all the internationally recognized weather models into a single package. They analyze it and develop first the deterministic weather forecasts for the next 15 days with the essentially with the grid of 4 by 4 kilometers worldwide. Now, the part of it is essentially behind it is the 87 different scenarios that different weather models develop routinely every hour. So they consolidate these models Next slide, please. And use different techniques, which I actually cannot say much. I'm not really an expert on that, to come up with the 100 probabilistic scenarios. So each scenario is effectively a scenario of the whole global weather. So we have 100 possibilities. They structure it such that they assign the probability of the same probability to each scenario. And effectively, these scenarios capture both the spatial dependency, spatial correlation, and temporal correlation. So effectively, if we take a location, for every location for the next 15 days, with a 1 hour time step, we can have 100 trajectories of what may happen in that location. And say trajectory number 1 is the same trajectory number 1 for every other location. Now, they say 15 days, technically they admit that probably 5-7 days when it's really realistic. Beyond that, the divergence becomes too big. So the idea is like we take this and we translate it into the sort of the weather to energy transformation. Next slide, please. I'm gonna skip this few slides because there is a reference to the paper where you can find more details. I really don't know all the details about this. So what we do for MISA, every day we call on the IBM API and we get the forecast for approximately 2,000 locations, just in case, not that we use all of them, but it covers every wind site, every solar site, every weather station, and also we got like all the cities and towns within MISA footprint with a population of over 20,000. So pretty dense coverage, just in case. We actually started from December of 2020, we started collecting all this forecasts just for research purposes. So next slide. So then what we do for the load forecasting, we ultimately develop machine learning technique very similar to what we listened yesterday to what PGM was presenting using XGBoost machine learning technique. So we do similar things to develop sort of 5 to 7 days scenarios of load by different zone within MISA. And for every wind site and every solar site, we develop 100 scenarios of wind output and solar output, mostly using kind of standard technique power curves for wind, but we assembled good public source data on a side-by-side basis and use essentially NREL's APIs to do the solar forecast. But we do, again, 100 scenarios of those. Next slide. Next slide, please. So the next step, we actually have the machinery that we had before we started the project, which is called analytics powered by PSO. PSO is the production costing engine, which Polaris developed, and it does all the security constraint unit commitment and dispatch optimization. And we provide the parallelization of all the computation on AWS cloud. So for us to bring up, hundreds of thousands virtual machines and run PSO in parallel is an absolute routine thing. So the Monte Carlo simulations are really very amenable to parallelization because most of the simulations are independent. So Selin is going to talk more about how it's actually done because, next slide, please. Even if we look at this structure, if we have 100 weather scenarios, and then we have, say, 1,000 draws of random outages, that creates 100,000 possible simulations. And when you try to run a unit commitment 100,000 times, I mean, we can do it. It's just going to be very expensive. We can bring enough machines. There's enough machines on AWS to do it, but it's just going to be very expensive to do. So the idea is it has to be done in a very smart way. Next slide, please. So generally, again, what we're after are the tails of the distribution, right? So there is no point to try to evenly go through the entire range of uncertainty and sort of with the same level of effort, right? If we can identify the way to focus more on the tails and less on the mid-range of the distribution and dedicate our computational resources more to the tails than to the mid-range, then we could significantly reduce the amount of effort spent per unit of precision and do this computation such that they become economically affordable. Next slide, please. So actually Selin is in her presentation will go through the detail sort of logic of how it's done. And it would turn out that initially we thought that we would only focus on like say being able to do this study for the next day or several days. Turns out that with the same technique, we can now run like annual assessment of resource adequacy at the nodal level. Because this technique turns out to be very, very scalable. So kind of the thing like running resource adequacy nodally is becoming absolutely affordable reality. Next slide. So what we provide as a part of the platform is also visualization of how the adequacy locationally spread over the territory of MISA. We look at all the things like what's the ranges for individual and aggregated wind and solar output, the load ranges, the net load, the availability. So kind of all the basic metrics in terms of your basic supply and demand, we can look at sort of an aggregate for every zone in MISA. Next slide. But we can also look at things really focused, identify where the pockets of reliability problems are, and also identify which resources are really helpful in solving the reliability problem and which are not because they are trapped behind the transmission constraints and they cannot be, at the time of scarcity, cannot be delivered where you need the energy. Next slide. So in terms of the metrics that we report, we do all the traditional metrics just to be sort of consistent with what people look at. And at the same time, we provide a whole bunch of nodal metrics. The reason is that effectively, if you think about it, all we are doing, we are computing the same kind of LMPs, but for reliability. And all the nodal mathematics that we are familiar with in the energy market, it actually has very meaningful interpretation when you start looking at reliability. All the reliability rent is instead of congestion rent. The value of transmission in delivering energy at time of scarcity. All these characteristics have their own economic meaning. So we just compute them and report them and allow to make them sort of visually accessible. So I'm not going to go through this. This is basically all I'm saying, that this is done. This is ready for use. We welcome partners to talk to us, and we'll be happy to work with everybody who is interested in implementing this technology. Thank you.
Thank you, Dr. Rudkevich. Any questions from our in-person audience? And reminder to the virtual audience to submit your questions via the Q&A feature in Zoom. A question? Please introduce yourself.
Sure. Emilio Pinto from DRW. Alex, can you elaborate a little bit on what is the SNAP metric means?
Oh, okay. So All right, let's see. So we have, imagine the following, we run 100,000 simulations, right? And for every simulation, we calculated the allocational marginal price. Now, for vast majority of the simulation, and then that would be the LMP T omega. Now, there is also, let's say before that we ran, the unit commitment day ahead market, and we've got what we call the base LMP, right? So for vast majority of the simulation, the difference is essentially like the noise, right? But for the instances when we see significant, shortages in the system, like load shedding, that load shedding starts setting the price. At that point, we see significant price spikes. They are locational. And effectively for every node, that's the difference, which is effectively the value of reliability at that node.
We have another question.
Mort Webster, Penn State. Thanks, Alex. This is really impressive stuff your team has put together. I'm a big fan of probabilistic methods. I have one technical question, one practical question. So the technical question is, as you well know, there's a difference between a Monte Carlo approach, like what you guys have currently implemented, where in every scenario at every point, there's different things that could happen, and then your software is simulating different dispatches and different commitments. And that's not always the same as what a stochastic commitment or dispatch would do. I'm curious whether in future iterations you guys have thought about also moving even further. That's harder, but like moving to, because the advantage of a stochastic dispatch within this, you would capture the option value better of, bringing a resource on. I don't know if you thought about that. That's the technical question.
We certainly thought about that. And actually the PSO that Russ developed has the stochastic unit commitment feature from day one. The issue is that we're trying to be kind of practical today. Today, there's no stochastic unit commitment actually run in any market, but we want to be helpful and provide as much information as practically possible today. Now, I can envision that the approach along this line, which helps to identify sort of the critical scenarios, would be informative, among other things, for actually feeding into the stochastic unit commitment, if that's based on scenarios, based on something else. So I can speculate now. I know, Russ, if you want to add something to that.
Do we have a question from online?
Yes, we do. Rajat, I'm going to unmute you. So if you could go ahead and say your name and ask your question.
Hi, Rajat Pungalea. So once nodes, firstly, this is super fascinating, so thank you so much. Once nodes are identified with the adequacy issues, what market mechanisms can be used or developed to resolve them? Like, is it how short-term or long-term is it? And then does the ISO solve them, or do market participants have the ability to do anything about it? Thanks.
Okay. Thank you. Great question. So technically, what we get a spot pricing for adequacy, right? So technically, we can imagine that there is a market administered by ISO where every generator gets paid that adequacy, right? When every load pays for adequacy, and the transmission owners get the adequacy rent. And with that, we may dream about deregulating transmission industry, right? Because they would be paid market rates. I'm just kidding. But in terms of, so essentially think about this as this is your spot pricing for capacity. And then you can have a forward market for that, but at least there is a spot pricing mechanism underlying it, which could be used to, mark to market all efforts. I don't think market participants would be able to use it. I mean, they could use it for sort of assessment of the market, but I think that you need some sort of centralized auctioneer to run the market.
We'll take our last question from inside the audience.
Russ Filbert, Polaris. And this is actually less of a question than just a clarification about stochastic modeling, because there's a lot of confusion about this. Probabilistic models can cover a lot of territory, and we can think of Monte Carlo and stochastic models as being two branches of that, where the stochastic models are enforcing a kind of a decision that has to be made across a number of different scenarios so that you have a robust decision. So the stochastic models are really about making decisions that are informed by the risk and are going to be robust. And that can be done through a stochastic model. It can be done through ancillary service policies. What Alex is talking about is really in the Monte Carlo world, because we've made a decision and now we're trying to test whether that decision is going to handle the issues that may come up. How well risk informed were the decisions, and do we need to go back and make them more conservative, or were they too conservative because we see absolutely no risks and we're wasting money? So understanding when Monte Carlo and stochastic methods are important, and when people talk about probabilistic methods, they don't always have a clear view of the distinctions there.
All right, let's thank our speaker.
And I don't need to answer that.
Thank you. Next, we'll have Dr. Selin Yanikara, who's an energy analyst at Newton Energy Group, and will also be presenting on stochastic null adequacy pricing. Please.
Good morning, everyone. My name is Selin from Newton Energy Group, and I wanted to thank again the FERC team for organizing this event.
Levon, can we get Selin's presentation up? Number 42.
Oh, no worries. Great. So my talk will be a follow-up to Alex's presentation. Alex introduced the methodology for stochastic nodal adequacy pricing and other probabilistic reliability metrics that serve as the economic signal for adequacy pricing and for different types of market participants. What I will follow up with is how do we realize and compute those metrics in a space of many weather scenarios and system outage conditions. Next slide, please. Slide, please.
Levon, can we advance the slide? Thank you.
So I'll reiterate what Alex said. So how has resource adequacy been done traditionally? It's usually used as a planning tool for annual assessment of capacity needs using simplified power system models as well as without detailed modeling of operational details. And because of that, not capturing the impact of operational details on generator availability, as well as not modeling the value of flexibility. So the question is, can such methods and tools capture the true impact of extreme weather events, those tail events per se? So question is, what are the needs from a tool and methodology for resource adequacy? And so next slide, please. So there are different decisions made in different timeframes, including short term that has different types of impacts on reliability. So the need is basically high fidelity models, both for the underlying physical system as well as operational details that will truly capture the availability and limitations of generating resources. An outcome from such a tool and methodology should be locational economic signals provided to different types of market participants that incorporate the value of adequacy. Next slide, please. So we mentioned there are different types of decisions in different timeframes. So what are the use cases for such a resource adequacy evaluation? So in the green box, we see a more traditional use case, so assessment of adequacy for annual system planning. So using our cloud parallelization process, this can be imagined as an annual simulation partitioned into weekly or bi-weekly segments that are run in parallel, incorporating multiple weather scenarios or multiple historical weather years. And we can look at decisions made in week ahead or day ahead time frame, like scheduling of hydro resources and scheduling of inflexible generation. So how can we define inadequacy event in such a resource adequacy use case? It could be insufficient capacity available for day ahead commitment. In the middle box, in the blue box, we can imagine a similar use case, but this time looking at the impact of decisions made in intraday in real-time time frame. So there we can be looking at inadequacy events that are insufficient reserves to respond to contingency situations or inability to replenish reserves in time. Another use case, which is what Alex presented, is more for short-term system planning for the next 2 to 5 days. So this is the Stochastic Nodal Adequacy Platform project that is being developed under ARPA-E. Next slide, please. So this is a more complete picture again for decisions made in different timeframes, starting from building and retiring decisions to real-time dispatch decisions. And for each of those, we would be testing different reliability impacts of different decisions. So if you look at week ahead and day ahead time frame, that would be assessment of the adequacy of the fleet itself. Whereas if you're looking at more at the day ahead and intraday time frame, that would be evaluating the impacts of non-recourse or inflexible decisions like commitment of inflexible generation and deployment of demand response and so on. If you look at more at the intraday and real-time scheduling, then we would be testing the adequacy of the reserve procurement policy. So it's testing the reliability impact of different types of decisions. Next slide, please. So Alex introduced the foundation behind this, but at the core of our methodology is spot pricing for adequacy that serve as the economic signal for load adequacy payment, payment to neighbors, and payment to generating resources, including storage. But I will be talking about how do we realize this computation that is essentially an expectation over many weather and outage scenarios. Next slide, please. Right. Resource adequacy is a probabilistic world, weather being the major uncertainty, as well as system outage conditions. So if we go back to Alex's presentation, SNAP is based on weather scenarios generated by IBM. Those are 100 weather scenarios, equally likely scenarios. And we evaluate each of them against multiple system outage conditions. So if we look at 100 weather scenarios and 100 outage conditions for each of those, that's a total of 10,000 scenarios. Next slide, please. So the question we're going to try to answer is, how do we efficiently evaluate tens of thousands of scenarios when evaluating the metrics? So the computational aspect to resource adequacy, we have multiple dimensions. There's the weather scenario dimension, the time period dimension for longer time frame evaluations, and there's the random outages dimension. So we have these three components when trying to balance the statistical significance and the computational burdens. Next slide, please. So we have two layers to this. If we look at the weather scenario and time period dimension, we employ a stratified sampling method to allocate our computational resources to those scenarios with shortage in proportion to their estimated shortage variance. So we're allocating our computational resources to interesting time periods and interesting weather scenarios. And the random outages dimension, filtering of those is based on an integrated scenario reduction that is done internally in the case simulation itself. So this is based on a simplified optimization formulation, and we'll start with that to see how that scenario reduction takes place. Slide, please. So integrated scenario reduction for random outage throws. The first step is base solution. So if we look at a typical day-ahead simulation that is solved every day by looking ahead a few more days. So we're making, for instance, Tuesday's decisions sometime in advance, sometime in Monday. And at that point, we're aware of some outages that started prior to that point, and we are able to take those into account when making decisions, commitment decisions for the next day, in this case, Tuesday. So the base solution is basically the commitment plan for Tuesday, let's say determined on Monday at 10 a.m., subject to known outages. So we take the commitment and dispatch decisions from this step, and then round one, which is a filtering of outage throws, is evaluating multiple surprising and random outage throws that start after we made the decisions for Tuesday. So these are the outages basically that we will have to address using the decisions that are available to be remade. So for instance, commitment of fast starting generation, dispatch of resources, and so on. So in this step, we employ a simplified optimization formulation that fixes some decisions to the base solution. And how complicated or how detailed this filtering of multiple outage throws is flexible. So we can include commitment or not include commitment, a relaxed commitment, for instance. So this step basically gives us those outage situations that lead to potential shortage conditions. And then only those ones in round two, we solve with the full SCOC and SCED formulation. And this step determines the actual outage throws with shortage, as well as it's used to calculate the probabilistic reliability metrics. And next slide, please. So we talked about shortage, but how is shortage defined? It's detected economically, but defined physically. So violations and excess prices, meaning whenever prices exceed anywhere in the system the shortage price threshold, that is flagged as potential shortage, and the shortage price threshold is determined by the user. So this allows us to flexibly define two major things. One, what is the order of actions to mitigate shortage? So do we shed reserve requirements first? Do we shed load first, or dispatch demand response resources and so on? and what events do we count towards shortage. So these two things we are able to designate by penalties that we attribute to violations, as well as the shortage price threshold level above which the event is detected as shortage. So if we look at the ERCOT setup, which is the market that we will use to illustrate an annual resource adequacy evaluation, we have a value of loss load of $200,000, a reserve violation penalty of $250,000, and a higher transmission penalty, meaning that if you look at the order of actions taken to mitigate shortage, it would be load shed first, and then shedding reserve requirements, and then violating transmission constraints. We have a shortage price threshold of $2,800, meaning that all of these events, if they were to occur, would be defined as a shortage condition. So the relationship between penalty prices, the hierarchy there, as well as their relationship with the shortage price threshold determines the order of actions as well as what is shortage. Next slide, please. So if we look at the filtering for the weather scenario and time period dimension, we employ a stratified sampling method there. At the filtering stage, we evaluate all of the weather scenarios and all of the time periods for longer term studies for shortage, basically evaluating them as detailed as the model requires. So it can be a SCOC run, it can be an economic dispatch run only. So evaluating them against some number of statistically significant enough number of outage draws. And then for those ones that exhibit shortage only, then we allocate further computational resources to them in proportion to their shortage variance. And then we reevaluate those scenarios. So in a nutshell, it's basically efficient allocation of the computational resources in hand. Slide, please. So this is a quick illustration of that two-stage method for stratified sampling. So in stage one, we have multiple weather scenarios. If we think of the IBM generated ones, we have 100 weather scenarios. And each of them, we evaluate some number of weeks. And let's say after we evaluated some number of outage situations for all of these weeks and all of these weather scenarios, we find that only 3 weeks in 2 scenarios, which are highlighted in blue here, exhibit shortage. And their variance contribution is, let's say from 50%, 30%, and 20%. Next slide, please. So in the second stage, we then reevaluate those weeks only in those 2 scenarios by allocating computational resources in proportion to their variance contribution. Next slide, please. So we evaluated ERCOT using an annual resource adequacy study. It's annual study with day-ahead decisions for 2024. And we partitioned the annual run into weekly segments that are run in parallel. And we included all 345 kV transmission constraints with a $200,000 of value of loss load. We don't have the weather scenario dimension here, so the goal is to identify the weeks and locations with shortage conditions. Slide, please. So our stratified sampling method to determine which weeks should we focus our computational efforts on gave us the month of August and November are problematic months in terms of shortage, meaning that we will allocate more computational resources to those months. And we'll see why that's the case. Next slide, please. So summary results for filtering stage, we use one virtual machine, basically for the whole year. We don't have the weather scenario dimension here. The second stage where we reevaluate those interesting weeks, we run 100 more. We use 100 more virtual machines and allocate those to different weeks and months based on their shortage variance. But one thing I want to emphasize is, so this translates into basically 10,100 day-ahead simulations. And the turnaround time for this annual run for this many simulations was less than 2.5 hours. And if you look at the total cost, the total cloud computing cost, that was $13 if we use spot machines and $57 if we use the more expensive on-demand machines. Next slide, please. So let's look at some geographical results. This shows 2 different days in August. On the left, we have a day where we have no load shed, but we still see a shortage due to excess prices caused by transmission constraints in the south. So we have a binding valley import interface that causes shortage in the south. And if we look at the right, you see the dark blue bubbles there, which show the load shed amount. So we see load shed in almost all major locations, except for some low snap pockets, meaning that there are areas where there's less value for adequacy. But overall, it's a more problematic hour. Next slide, please. Now we're going to look at a day in November. Remember that November was the month, the second largest month that we found that we should allocate our computational resources to. So this hour in November is very problematic. We see very high snap values all over and load shed. And we have outage situations where reliability issues are more economically resolved by violation of transmission constraints rather than load shed. So if you look at the reason to this, we see a graph here with expected megawatt on outage. Part of this is maintenance. So we have a large capacity of combined cycle units in maintenance, and combined with the lack of PV, we have a much more total capacity on outage than the August days. So that's why it's an extreme one. Slide, please. We can also look at generated performance. So this is normalized effective load carrying capability on demand, which is computed for each generating unit, and it's their expected value of this dispatched capacity at the time of shortage. So if we compare August and November, some points to point out is in November, we don't have PV. PV is not contributing, of course. We have less wind contribution in November compared to August. And if you look at combined cycles, which are the light blue bubbles, we see less contribution from them in November because of maintenance. And one interesting thing is storage, at least in these 2 shortage hours, is not contributing to alleviate shortage. Next slide, please. But there's another study that uses our tool that actually looked at that. So on the left, you see the shortage hours for each month in a future year. And on the right, you see after updating the storage operational strategy, the impact to a shortage, which actually alleviates shortage and reduces the total shortage hours in every month. Right, next slide. So to conclude, resource adequacy can be analyzed at a nodal level using high fidelity models, and we illustrated that for an annual study for ERCOT system. Operational details impact highly study outcomes. That was illustrated with another study using our tool. In our illustration, we used a nodal model with unit commitment, but only using 345 kV transmission. But other options can include inclusion of lower voltage transmission, so a more detailed model, or a less detailed model using zonal studies and economic dispatch only. Thank you. That was all.
Thank you, Selin. Do we have any questions from our in-person audience? Reminder to our Zoom audience to enter questions in Q&A. Please introduce yourself.
Hi, this is Jeannie Zhao from ISO New England. Great presentation. I have a question. It seems in your simulation, you can decompose each week separately and then run them in parallel. My question is, so for some resources, they run on limited fuel, for example, oil generator, and the oil consumption they use the week before will affect their performance in the following week. So I wonder if you have thoughts about how the parallel scheme can work for the resources with fuel inventory.
So one thing is that when we parallelize into multiple time segments, each time segment, we run some period before to initialize a generator status and initialize situations like you mentioned. And we are also able to control the level of parallelization. So if we have resources that require a longer time frame, like you said, we can use higher or longer segments when we parallelize as well. But we use some techniques to make sure we have reasonable initial status for each time period.
So let me see if I understand it correctly. So even you say you run just for a week, but you sort of have a pre-run period.
Right. Yeah.
Before the week.
Yeah.
To sort of properly set up the initial status for that week.
Yeah.
Okay, thank you.
Another question? Yeah.
This is Zizou from Argonne National Laboratory. So I have a question about the Monte Carlo simulation and outage draw. So what kind of uncertainty do you consider for that outage draw and Monte Carlo simulation and sampling?
So let me repeat your question. You said what kind of uncertainty we consider in our outage?
You're sampling from sampling from some distribution function, right? So that is represent some uncertainty.
Right. So in this model, we only had one set of outage rates that is basically an input to the model. And from there, from that probability distribution, there's sampling of the outage row. So it's based on outage rates. And
so for that outage rate sampling, I see that you sample 100 times, but the outage rate usually is very low probability. The failure rate is very low. So is 100 sufficient? The 100 number of samples sufficient to capture those low probability?
do you mind repeating the question?
Yeah, my question is that I see that you have 100 samples for the outage draw, right? But usually the outage, especially for thermal power plant, the probability of failure is pretty low. So that means that we need to have a large number of samples to capture that low probability events. Yeah.
Well, it depends on what you want to get at the end, right? Because if you have an ultimate metric that you measure, and what you really need to control is the precision with which you compute that metric. If you have some resources that have very low probability of outage, it may turn out that it just doesn't matter given the precision with which you want to get an answer. So I think that at the end, you don't really need to have every asset with exactly the same precision as long as you control the overall metric.
Follow-up? Okay. Do you have any questions from the virtual audience?
Not at this time.
All right. Any more questions from the physical audience? All right. Well, thanks very much again, Yelin. Lavon, could we please bring up slides number 43? And our next presenter will be Phil DeMello. He's Senior Technical Leader at Electric Power Research Institute, and he'll be presenting comparison of flexibility reserve and ORDC for increasing system flexibility. Philip.
Thank you. Yeah, so like he said, I'm Phil Mello with EPRI. I'm going to be presenting some work we did comparing the flexibility reserve with ORDC. If we could have the next slide, please. This work was part of a much larger project that was sponsored by the Department of Energy, where we had multiple teams working on different aspects of electricity markets, which we basically broke up by different decision horizons. So I worked on the shortest decision horizon, and we had lab partners with Lawrence Berkeley National Lab and Johns Hopkins University on our part of the project. NREL and Argonne were also participants in the larger project. And I also want to point out the bottom paper there, which will be published shortly. If you're interested in a summary of different flex and ramp ORDCs currently in use throughout ISOs today, that has a good summary of it, kind of pulled all the information together into one place. And hopefully when it's published, it's not too out of date because these things are always changing. So next slide. I'm going to be going through our motivation for this project, talking about differences and similarities between ORDC and Flex, talk about the reserve ramp sharing implications, and then showing some simulations that we did before the final conclusions. Next slide. So our project motivation is that there's an increase in there's a desire to increase the system flexibility to accommodate the additional variable and uncertainty in the net load. So additional wind, solar, but also things like rooftop PV and any sort of demand programs that may be impacting the load in ways that not currently expecting, and therefore the system wants flexibility to be able to accommodate it. We also want to compare the operating reserve demand curves, or ORDC, with separate products for flexibility or flex reserves, and then quantify the performance of them, any key differences, the parameters that make them unique or similar, using detailed operational simulations. Next slide. So kind of what I mean by flex or by ORDC. So by flex, I mean a new reserve product. So something alongside your regulation, your spin, non-spin, a new product called flex product, ramp product, flexi ramp, usually something along the imbalance reserve. There's a lot of different names for these sorts of things. So that's a new product. You get to define it how you want it, dispatch it how you want it. You have to come up with which generators can provide it, what attributes they need to have. And then when I talk about an ORDC, what I primarily mean is taking one or more of your existing reserve products, such as your spin or non-spin, and rather than simply procuring the minimum requirement at a certain penalty price, by adding this downward sloping demand curve on top of that to value additional amounts of that reserve that the system can provide. And so the ORDC represents that part of it. And so for this, again, that one's primarily applied to an existing product, and then the flex is a new product alongside of it. Next slide. So what we found is that really the difference between the two is whether or not a generator, the reserve products can share ramp rates on a generator. And what we find in most systems, reserve products actually can, that they allocate separate headroom on generators, but if a reserve has an activation time of 10 minutes, and the generator ramp rate is 2 megawatts per minute, it can provide 20 megawatts of that reserve. And that's what this graph is showing, is kind of 5 different cases of the energy and a reserve provision on a generator. And so in number 1, in the base case, we're providing 15 megawatts of a spin reserve out of a potential 20 megawatts that this generator could provide. It would be able to deploy that in 7.5 minutes, which is within the 10-minute reserve activation time specified by our reserve. If we applied an ORDC and ended up wanting to procure more of that spinning reserve, then this generator could provide an additional 5 megawatts of that spin. So it would use up its entire range of the spinning reserve. So it would be 20 megawatts total, deploy that in 10 minutes. If we, instead of an ORDC, use a separate flex reserve with the same specifications, but we don't enforce any sort of constraint to require the generator, the ramp rates to be separate for the different reserve products, then this generator could provide 20 megawatts of that flex reserve. And so, as you can see in 3, the 2 reserve types far exceed the just the normal ORDC, but also our spin limit from the ramp rate on this generator. As we move to 4, we can think about, well, instead of defining a separate product, if we relaxed our reserved activation time to 20 minutes and had the ORDC, well, now we're in a situation where it could provide the initial 15 megawatts it was, but it could also provide that full 20 megawatts that the flex case did. And in this case, it would still have a little bit of headroom because on the spin limit. And then in the 5th case, but of course, going back, the activation time for cases 3 and 4 is going to be greater than our desired 10 minutes. It's 17 and a half minutes for the 2. So the generator can fully deploy those reserves, just not as quickly as you would expect, assuming you would have, you would need to deploy them simultaneously. And then the 5th case, what we can do is put a constraint saying that not only the headroom has to be reserved on the generator, but also the ramp rate limits have to be maintained so that all reserves can be deployed within their target. And in that case, what we see is a flex that would only provide an additional 5 megawatts, similar to case 2. Next slide, please. So we did some simulations to develop, to demonstrate this. We used an ERCOT-like system that was developed from a 2012 case and kind of grown mostly with solar rather than wind. So it is quite a bit different than ERCOT today. We ended up running it with zonal transmission limits as shown in the picture. We did a 3-stage process to cover the major unit commitment and economic dispatch processes that you see in a market, defined basically as a day ahead with an hour ahead resolution, or within 1 hour resolution, 24-hour optimization. We used a 24-hour look ahead period to help with our storage dispatch primarily, and security constrained unit commitment. An hour ahead process, or really what would be a short-term unit commitment process as part of a real-time market, which had a 15-minute resolution, 1 hour optimization with a 3-hour look-ahead window. And then our real-time dispatch process, which has a 5-minute resolution and a 5-minute optimization with no additional look-ahead. We had different forecast errors for load, wind, and solar. And we targeted selected stress periods throughout the year. So when I show some of the results, there's going to be shortages of reserves that we see, and they're going to seem quite high, but this is only the selected stress periods. So on an annual basis, they're actually fairly low. Our primary scenarios were done with different operating reserve levels, like the Flex and the ORDC, and we used Plexos by Energy Exemplar. Next slide. So our operating reserve overview for these simulations, we have 4 main reserves that are procured in equal amounts through our day ahead, hour ahead, and real-time processes. Those would be non-spin, spin, and reg up for our upward reserves, and then reg down for our downward reserves. Our ORDC would add on to the base requirements of those cases, and our Flex would add a separate reserve for those cases for which we use Flex. We have static requirements for non-spin and spin, and then our regulation vary throughout the day and seasonally, as shown in the graph. Also, the reserves are cascading, so our higher quality reserves can substitute for the lower quality ones if there's no additional economic cost. Next slide. So for our simulations, what are the main differences between our Flex and our ORDC? So our Flex is a new reserve product. It was fashioned after our spinning reserve, so it has the same 10-minute activation, has all the same generators that can provide it. We determined its reliability or its requirement by covering 95% of the net load variability and uncertainty that we see. And we priced it at essentially 5% of the spin penalty price. So kind of what we expect the value of that to be. And we vary it seasonally, and we have 6 different blocks throughout each day. ORDC was very similar. We actually, we apply it to spin and non-spin. So that's in addition to the base reserve requirements of both. We don't change the base penalties on them. Our requirements change throughout the day in the 6 blocks and seasonally, similar to the Flex. And we developed price curves relating the percentile risk of each case and the requirement of that. But we split them among the 2 reserves. So actually, if it was not on spin and non-spin, the Flex requirement would be a point on the ORDC for the others. Next slide. So I'll talk about 7 cases total, but we'll do them in 2 sets. So just focusing on the top 3, our base case, which just has our 4 main reserves, doesn't have any additional Flex or ORDC. Our Flex case, which adds the Flex reserve, and then the ORDC case, which adds an ORDC to the non-spin and spin reserve. And so these were primarily focused on the impacts on our system flexibility. The next set of cases is really focused on comparing ORDC and Flex reserves to each other, and we'll talk about them a bit later. Next slide. So what we find is that both the Flex and ORDC are increasing our system flexibility. So if we look at the top graph, that shows our shortages among unserved energy, regulation up, and spin. And we see in our base case, we have actually rather high shortages as a percentage. And in our Flex case, we have almost no shortages. And then our ORDC case also has a very significant reduction. The lower graph is showing the dollars per megawatt hour of those shortage reductions. So obviously the base case doesn't have any reductions, so it doesn't have a cost associated with it. The Flex case came in at a little under $200. And the ORDC came in at around $105, both of which are below our lowest reserve penalty price, which was $250 for regulation. So they're both able to provide the system with more flexibility, reduce the shortages we see, and do it at a lower cost per megawatt hour than the system was willing to pay to alleviate those shortages when they occurred. If you look at this and say, well, why is Flex working so much better than ORDC? That's really because of how much spin is procured between the two. We found that in the simulations, the additional non-spin procurements didn't do very much in terms of reliability. I think that's mostly a simulation artifact, but I wouldn't take this to say that like, oh, Flex is much better at reducing or increasing system flexibility. I think the differences in the procurement amounts are too large to make that conclusion. But if we go into the next slide and start looking at our cases to compare them more closely, we ended up doing 4 additional cases. And in these cases, the top 2 are Flex-like cases, and then the bottom 2 are ORDC-like cases. In these, we decided to eliminate the ORDC on the non-spin because it wasn't doing all that much. We've now defined our Flex requirements using the ORDC from the spin. So rather than having a set requirement, it has that ORDC. And then we have an ORDC spin case where, again, the spin is using the same requirement. In the ORDC 20-minute spin, that's where we relax the activation time of spin to allow it to each generator to provide more of that reserve. And then in our ORDC-like cases, we have a Flex ORDC with no ramp sharing, where we add that additional constraint. So if we go to the next slide, what we see here is that with our 2 different strategies of kind of matching Flex and ORDC, we got 2 pretty similar sets of performance. So this is just looking at the provision of reserves above our, as compared to our base requirements. So as we can see, our base case is a little under 100% because it had shortages. And then when we add the ORDCs to the different reserves, they procure more. And then our Flex ORDC and ORDC 20-minute spin, they procure more than the others because we have essentially allowed each generator to provide more of the reserves. And if we go to the next slide, we can see how this impacts our 2 previous metrics. So we have our cost of reducing the shortages on the left, where what we see is that the 2 cases where essentially ramp sharing is enabled had a much lower overall cost than the other cases, less than $10 a megawatt hour compared to about $80 a megawatt hour in the other 2. Also allowing that ramp sharing had a larger effect on the shortages. It reduced them more, so there's less shortages overall. So they were both cheaper and more effective. But that's kind of on average, and there's an important caveat to that, which we'll see in the next slide, which is if we looked at the unserved energy in our system, that is an exception to kind of our average results. And what we see here is that actually when we allowed that additional ramp sharing, our unserved energy went up. And our unserved energy had the highest penalty price, was the thing we were trying to avoid the most. And so this is actually, this actually could be very concerning to your system. It turns out we looked into these periods where there was unserved energy. It turned out to be large solar ramps down of about 20 gigawatts of solar in 3 hours. And the system was trying to make that up. And actually it would exhaust the entire ramp up capacity it had. And it would still be holding some reserves. It just could not deploy them because it just needed so much up ramp. And so if that is a concern for your system, you would probably want to enforce this ramp sharing constraint or make sure you design your flex reserve with a short enough activation time to make up for that. And then we'll go to the next slide. So in conclusion, both the ORDC and flex increase our system flexibility, reduce shortages of unserved energy and other reserves. The key difference between the common implementations we found was that ramp sharing constraint between them. If they're able to share a generator's ramp capacity, that's more typical of a flex reserve. And if they aren't, that's more typical of the ORDC. And overall, kind of on average, that was sharing that ramp was better, but there were key times, especially during those short, fast ramping events, when that can be problematic to the system. And the table on the right, we go through a lot of the pros and cons of implementation of different of the flex and ORDC. Basically, you know, a flex reserve is flexible itself. You can design it to match your system needs. You're kind of locked into, if you're applying an ORDC to an existing reserve, you're locked into how that reserve is defined already, which generators can provide it. But that also gives you some reduced effort that you won't need to certify generators to provide that reserve. You already have that built in. But on the cons, you know, you definitely don't have the flexibility if your ramps need kind of a different reserve product. So there's a lot of things to think about. If your software is flexible, though, you can really choose either approach and make it work for your system. Are there any questions?
Thank you, Philip. Any questions from our physical audience? Maybe a question in the back.
Thanks. Mort Webster, Penn State. So it looked like you showed trade-offs between the reliability and the cost. Did you look at prices? Because one of the things about ORDC is that some people might think that's a good way to increase prices to offset the price suppression that other things that improve reliability tend to do. Did you look at that trade-off?
We did a little bit. I would say that kind of overall, and I don't like to draw conclusions about the prices from production costs too much, where you know, it's all based on, you know, you know, we don't have reserve bids in the model, so there's no behavior to compare against. But I did see that if you look just at kind of reserve prices and reserve revenue for generators, they both flex and ORDC actually increased the same, but or about the same. But what I saw was that the ORDC case also kept up energy revenues for generators, but the flex reserve had lower energy revenue for generators. So they may make it up on reserves, but they could lose it on.
Do we have any questions from the virtual audience?
No.
Right, one more question from our physical audience.
Thank you. So a couple of things. One, following on the previous question, the ORDC pricing is used primarily, not primarily, but to a great extent also as a substitute for capacity market in airport to provide revenues for the generator. So if you replace it with flex, would that also provide that mechanism? And the second part is the ORDC generally only apply in real time. So how does the day ahead in real time in your approach, in your modeling or simulate?
So, I mean, I don't want to comment on capacity prices because that was really outside of our scope. I think, you know, you'd really have to think about your market design if you want to use. I mean, I think the flexibility you get for the system through these mechanisms, you know, is justification enough to have products and pricing to support that. I don't know that you want to shoehorn additional capacity payments into that mechanism. That could potentially distort other prices because these prices have to work with, you know, the overall bids and marks in real time. And then on timing of reserves, yeah, I think that's true that there's a lot of differences in how these reserves are procured in different ISOs. For what I presented, we really chose to get them in all three because we wanted to have the least differences between the different stages so we could really focus on what the reserves were doing. We did other simulations where we looked at different procurements and different reserve or in the different stages of the simulation. I found that it will really depend on your system because if you need to spin up long start capacity that in a day ahead time frame, you may need to procure your reserves day ahead. But for our system, we had a lot of quick start capacity, which we could procure hour ahead. And so that had the biggest impact on our system. Only procuring in real time, and this is potentially just a modeling deficit because our real time is really focused on, it can't commit additional units and it's only focused on that next 5 minutes. So we found if you only procured in real time, it did have a positive effect on reducing shortages, but it was generally lower than if you had procured them in previous stages. So.
One more question from the in-person audience.
Hi, I'm Emma Nicholson from FERC. Thank you very much for this presentation. It's very informative. I have one follow-up question and for sort of the comparison of the two, which are seemingly quite similar. We hear a lot about the importance of the timescales of the uncertainty and the myopic real-time dispatch where you might sort of inefficiently burn some ramp and that might be intertemporally inefficient to do that. So do you see any benefits to sort of having, like, a flexible ramp product, it would seem you could have a 20-minute lead time or even an hour lead time like the SPP uncertainty product and sort of compare some of those flex products that are more longer term versus, so that type of longer term flex product and having an ORDC versus with 10-minute reserves versus a 10-minute flex product and a 10-minute ORDC, which are essentially identical products, right? So I know it's like a really muddled question, but it would seem that to me that if you had a flex product on a different time scale, you would be able to do a better intertemporal optimization of your ramp than you would if you were only using a 10-minute ORDC. If that makes any sense. Thanks.
Yeah, I do think that makes sense. We didn't look at that in the simulation, so I can't say definitively, but I agree with your hypothesis that, and I think that is one of the benefits of choosing to use a flex product is that you can target that time scale towards what's important for your system. And I think there's kind of two important things to that. You may want to do two flex products, one with a short duration to make sure that you have a high ramp rate for the very fastest ramps, but you may be encountering, fairly consistent, like 2 or 3 hour ramps from solar production that you also want to make sure you have enough duration to cover. So I could see them being layered that way and being very effective.
Thank you, Philip. Our next two presenters are going to be virtual. So we'll ask our next presenter to share their screen, and that will be Andres Ramirez Aria.
Yes, I'm just testing the audio right now.
Yes, we can hear you. Sounds great. Can you also turn on your video?
Yes, just give me 1 second, please.
Sorry. Oh, never mind.
Apologize for that. Do you hear me now? I was just having an issue with my audio.
Andres, if you're speaking, yes, we can hear you.
Perfect.
Oh, I'm sorry.
I'm gonna share my screen. That's correct, or you want to share? Or...
Yeah, if you could please share your screen using the share content button. It's the green button at the bottom of the Zoom window.
Yes. Yeah, I'm sharing my screen right now. Could you confirm with me?
Yes, we could see it. Is this Andres, Philippe, or is it Alberto?
So yeah, so Professor Alberto unfortunately couldn't make it today at a last minute situation, and I'll be talking on his behalf on this presentation.
Great, thank you. Just confirming.
Yeah, I know.
Go ahead.
Professor Alberto is also on the call, so in case there's any questions, or I don't know, Professor, if you want to present, that's fair as well.
Okay, if could whoever's going to present please turn on their camera?
Yes, just 1 second.
Also, if you could full screen your PowerPoint.
Thanks. Yeah, if you can swap the display setting at the top of your screen.
Yes, I'm working on it. I apologize. I was not expecting that I had to get the screen, so just bear with me for 1 second. Just gonna share my. This should do it.
This looks great. Thank you.
Perfect. I'll turn my camera in just 1 second. Just adjusting the video settings. I do apologize. It's a bit dark. I'm on the West Coast, so it's a bit early here. Great. So thank you for bearing with me while I was trying to get the presentation ready. This presentation is the objective of this presentation is to talk about ABSCORES. ABSCORES is a novel application of a banking scoring system in rating electricity systems. Basically, the main objective of the project is to understand or to quantify some measure of risk for energy generators in the unit commitment problem or intra-hourly commitment of energy. The content of this presentation is gonna cover 4 key milestones. The first one is gonna be that project description, and the second one is gonna be the methodology. The third one, the risk scores, and the fourth one, the impact and importance. Something that I want to start talking about is the goal of this presentation is to explore the machine learning side of this project. This project involves several teams that are working together to produce the results that I'm going to show here. One of those presentations already happened in the other session. Was called Uncertainty Informed Renewable Energy Scheduling, a scalable by level framework for anybody that is interested. And this is basically the optimization procedure that we are using. This just to give a quick overview, because I believe it's important for the sake of this presentation. This is just this optimization problem tries to overcome the variability of variable renewable energy sources using a novel technique based on McCormick envelopes and strong dwelling. And that's the optimization technique that we are using here. And for the results that I'm going to show today, however, I'm not going to be talking about that particular methodology. I'm going to be focused on the machine learning side or the statistical side of estimating the risk scores. So let me start talking about a bit about the introduction or the motivation around this project. The increase on intermittent renewable energy sources is forecasted to increase the usage of batteries and generate more curtailment on the system. So if you look at the first 2 charts on the left here, you've got the reference case for 2022 and the reference case for 2050. And you can see the increase or the penetration of renewable energy sources into the system. The penetration of renewable energy sources into the system, as all of you might be aware, is basically generates an influx of variability. And the main objective of this project is to quantify that variability or that risk that is being injected into the system and generate an accurate and way of measuring risk. That's the objective. The Lehigh ARPA-E ABSCORES project is a risk scoring system for energy generators, prosumers, among other stakeholders that interact within the system. The objective of this particular measurement is just to give a risk score or a measurement of the performance of a particular energy generator in the energy commitment problem. You see here on the top left, we put a chart of the risk score, and as you can see, this score resembles a credit score. The score we estimated, I'm going to walk everybody through the methodology we assessed, but the objective is to generate a score between 300 and 850 that basically is telling the users how risky or what is the likelihood of an imbalance of a particular generator or a particular generator not dispatching the energy commitment that they made or the contract that they signed. As I mentioned before, we're trying to quantify the likelihood of imbalances from that inclusion of renewable energy sources. I believe it's important to clarify or to define what our measurement of risk is. So our measurement of risk is the likelihood of deviating from a contract or triggering ramping constraints for both energy and ancillary services for stakeholders. It's important to notice here that the objective or why this is important to measure is because this can lead to power shortages or financial losses from the users of the network or the stakeholders in the network. We decided to put this phrase here, and I think this contains the importance of the project, and is that energy commitments and risk management go hand in hand, and a deviation in one can lead to a blackout on the land or on the other. So the main objective of this project is, as I said before, work with the energy commitments from generators and establish a risk measurement that will allow all the stakeholders to be informed and to improve their decisions. So I'm going to start talking about the problem now. We focus on the table of the left. You'll be able to see that this project aims to develop the risk score measurement using the security constraint economic dispatch and security constraint unit commitment optimization results from the New York ISO 1576 BOSS system. And there are basically three big steps on developing this risk score and using this risk score. The first one is the energy commitment, and this is going to be the output of that optimization model. Something that I have to also mention is the fact that we are using renewable energy sources simulation and load simulations of the future in order to create this or to obtain these optimization results. After that step, we estimate the risk score, and I'm going to walk you through that in a couple minutes. And after the risk score is developed and is being tested and evaluated, we use that risk score to constrain or limit the operation features of each generator. Basically, the maximum output or Pmax that they can output into the grid or commit in their contracts. That's the structure, the three steps that we're taking in order to calculate and then integrate the risk scores in the energy grid. The risk scoring methodology that I'm going to be covering today is a two-step process. The first step is running or estimating the optimization results from the security constraint unit commitment and security constraint economic dispatch for several scenarios. These scenarios, again, are assessing the variability of renewable energy sources. We've got 1,000 scenarios, and we select a significant portion of those scenarios to run the optimization procedures. So for each one of the scenarios, we've got results around the output, costs, operational features of every generator for every hour of a specific day. With that information, then we proceed to use machine learning classification model to estimate that likelihood or probability of not committing or not supplying the energy commitment that each generator made for each hour of the day. This is an overview of the methodology I just described, and I'm going to walk you through this methodology step by step. So the first step is the forecasting module. The forecasting module basically establishes how energy renewable sources will look in the future. We're taking as a case study to the year 2030, and we're also doing forecasting for the load. As I said, we create 1,000 scenarios, both for renewable energy sources, this is solar energy and wind energy, and for load. This information, a set of these scenarios, 200 of them, are passed to the optimization model, which, as I mentioned before, the security constraint unit commitment and security constraint economic dispatch work together on a bi-level optimization process to generate the operational outputs or characteristics of these generators. So basically, we get as a result ramping amounts, operational costs, and other features that are relevant for the machine learning model, right? These first two models are assessed by the other parts of the team. As I mentioned before, this team combines several groups. The optimization model is being assessed by the MIT group, and the forecasting model is being assessed by Livermore and one of the other teams in the project. I'm gonna now slow down and talk in detail about the machine learning model. After we get the results from the optimization module, we start with feature engineering. This feature engineering consists of setting up the required data, extracting the data from the optimization module, and constructing our database of each generator for each hour of the day for every scenario. Each one of these data points contains, as I mentioned, operational features that are output of the optimization model. After the feature engineering is completed, we use a methodology that is common in credit scoring, which is known as weight of evidence and information value. And the reason that we use this information is to create a feature binding. The reason we're using feature binding in our project is because we want to facilitate or streamline in a better fashion how each feature affects the score. We want to be able to quantify how a particular feature of every generator for every hour of the day is elevating or decreasing the risk score for each generator. So these first two steps you will call are the feature engineering steps of our mechanism, machine learning mechanism. And after this is constructed, then we follow or continue with the machine learning training pipeline. This pipeline consists of standardizing data, creating the required tests and training data sets, and then doing a training of several statistical models. These statistical models are tuned, their hyperparameters are tuned, and then they are compared for performance. The best model is chosen, and this model basically outputs the probability of an energy generator having a deviation from their unit commitment. A deviation above, we have a specific threshold, and a deviation above that threshold is something that for this particular model is negative. A deviation below that threshold is, we could call it positive, or at least is not negative. And this model is assessing the likelihood or probability of having a deviation that is above the threshold that we estimated. The output of this model, again, is a probability from 0 to 1. And then the next module of the machine learning pipeline is the scorecard generation, which basically uses this probability and then creates a numerical transformation to output that risk score that we are more familiar with, which is a range between 350 and 850. So this is the risk scoring methodology pipeline that we are using right now in order to, from the forecast of renewable energy sources and load through the optimization model, being able to output a risk score for each generator and for every hour of the day for our testing period. So just again, a brief look at the model output, which is the key development of this project, is the risk score, which lies between 300 and 850. An energy generator for a particular day with a score close to 300 is likely not to meet their energy contract. An energy generator close to 850 is very likely to meet their energy contract. So as you can see, it works similarly to what a credit score means or produces. Closer to 850, it's more reliable or is more likely that that energy generator would meet their commitment and vice versa. So I'm going to walk you through one example of an energy generator just to show in detail the construction of the risk score. So this energy generator is located in Manhattan, New York. It's a natural gas energy generator, and the evaluation day or the testing day for this presentation is August the 2nd, 2010. Right here, you can see the location of that energy generator. So one of the outputs of this project is the hourly risk score. The chart on the left has the composition of the hourly risk score for this particular energy generator. And you can see here how the risk score changes over time. The blue dots are the average risk score, and the black confidence interval shows how this risk score changes over time. I just realized that before was a typo. This energy generator is not natural gas, it's a wind energy generator, as you can see by the title of the chart. So the wind energy generator is experience high variability, as you can see in the chart on the top right. And this variability arrives from the wind speed variability. Wind speed variability through the course of the day is high compared to an energy source like solar energy, which you can find on the bottom right. Solar energy, for instance, at night has no variability as the phenomena, we cannot experience the phenomena, or at least not from direct solar irradiance compared to a wind generator. So you can see how the profile for this generator is constant and the risk score is fairly low. Before I move to a comparison between different field types, we also generated a decomposition on how each feature affects the risk score. For the sake of this presentation, we removed the name of every feature, but as I mentioned, these are the features that are output from the optimization model. As you can see, through the course of the day and every hour of the day, every feature has a different impact on the risk score. Some of those features have a positive or negative impact, and the effect changes over time. This is the chart that I wanted to talk about in detail, and is how different generators from different fuel types interact during the day. This chart is a little bit convoluted, has a lot of information in it, but I want the viewer to focus on a couple of things. The first thing is the bottom, I guess, orange or peach toned risk profile, which belong to the wind energy generators. I'm going to try to annotate here, take advantage of the virtual environment. Here on the bottom, you can see the energy generators that I'm referring to. As you see, the wind energy generators have a fairly constant risks profile that is along 450. And the reason for this is, as I mentioned before, the profile of wind energy that is has constant variability throughout the day, throughout all our scenarios. If we take a look now at our solar energy generators, which is this blue line or lighter blue line here, you can see that their risk profile matches the solar variability profile, which is whenever we see solar irradiance, the variability increases, and as a result, the risk score gets worse. This is aligned with our proposition from the beginning that a low score is connected with a chance that these generators are not likely to meet their energy contracts. Now, the interesting thing here with this chart is to show how all the other types of generators, in particular natural gas, interact with the renewable energy sources. As you see, the red lines in the middle between 650 and 450, they are moving or adjusting during the day. And these adjustments are an effect of solar and wind and renewable energy sources penetration. Lastly, I would like to point out that a more or less, call it risky generator as nuclear power that has less chance of ramping up or down has a great score overall for this particular testing period. As I mentioned before, this is just one day, but we generated scores for a whole week for every generator for every hour of the day.
Hi, Felipe, just a warning to get close to wrapping up. We're about
just one slide. Thank you so much.
Thanks.
So just to finish here, the importance of the project, three main points. The first one is grid stability, supporting the support grid stability. Basically, we want to minimize ramping ups or use of or overuse of energy storage facilities, renewable energy reliability. The ability to forecast this risk score will allow not only the renewable energy generators, but other generators to assess the variability of renewable energy sources better. And finally, the access to data. We generated the ABSCORES desk, which is an interactive dashboard that basically shows some of the results more in detail, and the user is able to explore these results. This is the QR code for you to explore this demo or this video in detail that will show our results, just for the sake of time. Thank you so much.
Right, thank you, Felipe. Do we have any questions from our in-person audience? Reminder to the virtual audience to submit questions via the Zoom Q&A feature. One question from an in-person.
Russ Forward, Polaris. Just a couple of methodological questions. You mentioned bi-level modeling. Were you referring to your forecast module versus your learning module, or you were talking about UC versus ED?
The bi-level model is the optimization model. That's what I refer to when we talked about that. I don't know if Professor Alberto is also in the call. I know maybe he wants to also clarify that.
I don't know that I understood. Was it one or the other, or was it something else?
No, the bi-level is nothing to do with forecasting and then the optimization model. When I mention bi-level, is that the optimization framework that we're using is a scalable bi-level framework.
So it's like Lagrange relaxation.
Yes, as I mentioned. I apologize because that's out of the scope of this presentation, but it's just the methodology used to
solve the unit commitment. Okay, I got
correct,
it.
Yes.
Thanks. So you also mentioned that you're using a New York model. What's the province of that? That sounds like an interesting thing to be able to have. And I assume it's an open source or non-proprietary model.
I wouldn't have the information right now, but I can get back to you. This is the New York ISO system. So yes, I'm pretty sure this is an open source grid, but the model itself is not. Before this presentation in the other room, we were exploring the detailed methodology that we're using to optimize this system.
Okay, I'll follow up with Alberto then about the data sets, because that could be a very useful thing to make more publicly available. Thank you.
Thank you.
We have a question from online.
Yes, Richard, if you could unmute.
Yes. I'm trying to clarify what I think I saw in your presentation, that you said that there was a generator in downtown Manhattan, and then on the next slide, it appeared to be a wind generator. Are there wind generators in downtown Manhattan?
No, Richard, I believe that that's a problem with this slide. We decided to use a wind generator instead of a natural gas generator, because the risk profile is more consistent, so it was easier to explain. But no, of course, there's no wind generator on the middle of Manhattan. That map that I showed, that generator was a gas generator. However, unfortunately, we didn't change the map to reflect where the position of the wind generator was.
And the that spaghetti chart that you put up seemed, and maybe I'm overreading it, seemed to have the natural gas score as a function of renewable output, probably mainly solar. Does the score for an individual generator change based on the fact that it's getting redispatched, which is, which is an interesting question because it could have self-scheduled, which would have created another problem. But giving the ISO the flexibility to redispatch that gas generator shouldn't affect its credit score.
Each generator acts independently. The information that they have are just costs and load demands. But for instance, a natural gas generator, it really has no information about the contract of a solar energy generator, for instance, or the information that they are seeing. So they are independent in that way. So the model itself is not, it's just a machine learning model that uses the information of each generator separately to estimate the risk score. So that interaction or complementarity you see on the output of the risk score is just an effect of the correlation of the unit commitment from the natural gas generators and the solar energy generators.
Yeah, but why should the natural gas score be a function of solar output?
Usually the risk score for instance, a natural gas generator, I think this is something that is important, changes just due to the ability of a natural gas generator to ramp up or ramp down. Contrarily to a nuclear energy generator, the costs of ramping up or ramping down are sustainably lower. Now, it's important to say that the fact that the risk score for a natural gas is lower, it doesn't mean that the generator is riskier. It just means that this generator is basically using this variability to arbitrage or generate an opportunity of generating more energy. So it's important, I believe, that distinguish how we interpret this risk score from renewable energy sources versus non-renewable energy sources.
I certainly agree with you on that, but the fact of the matter is that natural gas gets a lower score for being flexible. It looks, at least that's what it looks like to me.
Yes, but as I mentioned, Richard, the fact that the risk score is lower is a reflection on how these generators are taking advantage of the variability of solar irradiance to sell more energy. It's not that the energy generator is less, we can call it efficient. It's just that it's involved in more risk because it's taking advantage of the variance of renewable energy sources.
Okay.
Thanks for the discussion. Do we have any more questions from the in-person audience? And no questions from online? All right. Well, thank you very much, Felipe. And I'll now ask our final presenter for this session to share their screen. That will be Petr Svoboda. He's an engineer at Unicorn Systems, which is based in Prague in the Czech Republic. Petr, can you hear us? Yes. Oh, I see you're already online. Thank you.
Yes.
He'll be presenting recent developments in the day-ahead and real-time electricity market design and software caused by the higher energy costs and emerging technologies, the European experience. Take it away.
Yeah, good afternoon from Prague in Czech Republic. My name is Petr Svoboda. I've been working for Unicorn Systems for over the last 20 years. And now in next 20 minutes, I'd like to share with you some experience and recent developments in the electricity market in Europe. I'm really glad I can be here and I could listen to the previous presentations, because for me personally, it's very important to share that experience even between US and Europe. So I hope that my presentation will also give you some inspiration. Okay, Unicorn system company which I'm representing has been established in 1990. Since 1995, we are working in the energy sector. We have delivered hundreds of solutions for the companies across Europe. The services are provided by 2,400 developers or other IT professionals in our 25 development centers. And thanks to these more than 20 years of experience in delivering the solutions, we have really unique position in the supplying the IT solutions or systems for European system operators for the coordinations or initiatives they do on international level, and also for local and regional utilities. Actually, vast majority of the projects or pan-European solutions and integrations which I'm going to present to you today were delivered by Unicorn, or were delivered by Unicorn with some other cooperation, so either as a whole or a part of the solutions. Okay, and that was for introduction, but now let's jump into the European electricity market. And I have to say it's quite a complex environment. We have 36 countries with their national legislation, usually also some national language. And we have over 40 system operators. Here I mean really those operating the transmission grids on the voltage level of 220 kV or above. And those countries and system operators are actually split into 5 synchronous areas. And the cooperation and coordination, it's made possible with the help of 6 regional coordinators or coordination centers. Despite of this complex, difficult environment, still there was successfully developed deregulated single European day-ahead market, and it was mostly due to some pan-European or regional initiatives. There are more of them, but mostly from time constraints. I will focus on 3 areas, and that will be for the transmission capacity management or allocation, for the capacity markets and grid balancing. There are some other initiatives. Worth to mention definitely is the operational security coordination and really preparation for the real-time operation. If we look into the transmission capacity allocation or management, the single European electricity market by design must allow commercial trades between any European country. So you can be the producer or consumer in any country, and you should be able to put your bid into some national market, but to make the trade with any counterparty. And the transmission capacity cooperation, it's on the side of the system operators, and it's about translating the transmission capacity limits into the limits which can be evaluated when putting the commercial trades or bid into the market. Yet the provided capacities obviously must ensure that the grids are operated in a secured way. In the past, there was the transmission capacity expressed explicitly as a capacity limit on the border between two countries, between two bidding zones. And you, as the market participant, if you wanted to perform some transfer or to transfer the energy to different country, different zone, you would need to explicitly get the necessary capacity on every border your energy would be crossing. This was later on replaced with the implicit capacity allocation, but yet with this limited way of expressing the limits just by a single limit, transmission limit on the border, which was recently replaced with the flow-based approach, which is definitely nothing new for you knowing the US market and how it operates. But here it's not calculated just by a single system operator, but the flow-based approach has been applied in the wider region consisting of 16 system operators in 13 countries. And they have a common IT platform in which they, on a daily basis, provide the data and run a coordinated calculation which provides or identifies the critical network elements and calculates the power transfer distribution factors, which can be then passed for the daily market. And this is done really in cooperated way through this central platform by all these transmission system operators. And as a result, this flow-based approach can or is utilized for the single European market coupling, and it's one of the cornerstones allowing that free trades between countries. So very interesting initiative, interesting cooperation of system operators. And to demonstrate you some of the benefits or some of the results. So over those are the results over the last 12 months. The price convergence has been achieved. The full price convergence has been achieved in 27% of hours, and actually the price spread between the bidding zones is below 25% and 56% of the hours, meaning that in all these 16 system operator areas, 13 countries, the electricity prices for the producers and consumers are very similar. And that was one of the goals of having such an approach, to maximize the social welfare, because it really creates the much larger market for the buyers and sellers where to put the bids, and better prices with no discrimination of your location because once you are in this region, you see that in 56% of the hours, you would get probably the best, or definitely economically, optimally the best price for all, considering all the bits in that region. And of course, the transmission capacities and the grids in general are available in maximum, but still the grid is operated safely. I say the better prices. I have to comment that obviously in absolute value, the prices were pretty high, and you can see that in some months there were really like up to the 400 euro and per megawatt hour, and in some hours even higher, but that was not caused by introduction of the floor base, but other aspects and the energy crisis in Europe. Because the European market has been already decoupled, liberalized, the system operators are responsible for operation of the transmission grid, and they cooperate in this initiatives like flow-based core project to calculate the transmission capacities in coordinated ways, but they are not responsible for operating the energy markets. That's another entity, power exchanges. They are typically at least one in each bidding zone. In a simplified way, you can imagine that it's like one country, or in some countries there are multiple bidding zones. And there is one nominated electricity market operator, one power exchange responsible for the first one, but they are allowed multiple power exchanges per bidding zones. So there is a competition, and the customer who is buying or selling the energy can decide on which company, which power exchange is better. But also the power exchanges do have a common IT platform. They do cooperate in so-called price coupling of region projects. They have a single algorithm, which is called Euphemia, and that algorithm is used to calculate the power prices across the Europe. So the power exchanges expose their services to the market participants, but the bids are then put into the shared common order book and evaluated in one optimization algorithm. That market coupling, it's running 4 days ahead. There is also an intraday time frame. Currently, or it has started in 1 hour resolution, but slowly some countries have already switched to 30 minutes or 15 minutes. It should be completely switched to 15 minutes market time units in 2025, based on some EU regulation. That was for the system operators and transmission capacities, for the power exchanges and their cooperation and initiative for the electricity market. Now, if we go further for the real-time markets, there are again some 3 important initiatives by the system operators called Libra, Mare, and Picasso. All of them are already live, and those common platforms are there for exchanging the different products for the balancing. So Libra for the replacement reserves, RR, Mare for the exchange and activation of the manual frequency restoration reserves, and FRR, and then Picasso for the automatic reserves. And the idea behind this platform, these common platforms, it's really that the activation and procurement of the reserves is again with the maximum social welfare by having that procured on the common market. And there are just standard products, as I said, AFRR, MFRR, RR, with those activation times, so ranging from 5 minutes, 12.5 minutes, and 1 hour. But it's not mandatory. So these system operators can still have their own markets with some specific products if they need to. But if they want to achieve a larger area, better prices, they can join and adapt to this standard products. Apart from the standard AC or high voltage AC transmission grid, there are really heavily used high voltage DC cables. And those DC cables are often, well, either connecting to some offshore wind farms, but a lot of them, it's really operated in a commercial basis, connecting some synchronous areas. And you can explicitly buy some capacity in them in long term, or they are implicit part of this day-ahead market, or even providing some balancing services in some cases. For some of these cables, mostly those which are between or which have one end in the UK, we do deliver a solution for HVDC management. The challenge in there is really translating the market results, which are, as I said, mostly in 1 hour resolution blocks into the signals to ramp up, ramp down the cables. So it's a optimization kind of simple one, but still important because the technical and limits and ramping limits cannot be exceeded. So we do have such a solution also for real-time monitoring, signaling the cable notifications, and of course also to be able to communicate with the other platforms, like with the markets and with the platforms and system operators. And my last slide. We have heard also this morning a lot about flexibility. The same, it's obviously said or discussed a lot in Europe, mostly because the amount of distributed energy sources, the electrical vehicles, but also the decommissioning of the coal power plants and not enough new nuclear power plants being built. So the flexibility is important, but the opinion of the way where we are heading, it's that we provide this solution for the new emerging actors, like the providers who are not active on the market, but having some flexibility in generation consumption, and could be even the households, with some aggregators who can really be the umbrella for those providers and provide that flexibility to the markets, meaning that from the system operator perspective, still these aggregators can fit into the existing products and existing processes and just provide that flexibility through that, and just get some money through to the fact how they get the flexibility from their providers. So that's all from my slides. Thank you for your attention, and with, I guess, some space for questions.
Thank you, Peter. Any questions from our in-person audience? One question. Please introduce yourself.
Russ Feldberg, Polaris Systems Optimization. Thank you for the overview of the things going on in Europe. It seems that the market continues to evolve in a more detailed way in what we in the States would call pipes and bubbles representation of the transmission system. Do you see that reaching its limits? And is there understanding of maybe the importance of, or maybe of evolution towards a more nodal market design?
Actually, I think that that flow-based approach, as I've presented, is coming or is already very close to that nodal design, because actually the computation which is behind it's already considering the physical substations and the electrical nodes they represent and the branches. And internally, the algorithm already knows even the nodal prices, but it's just not exposed to the market because the market is still used to the bidding zones, as we call them, and they are larger. But indeed, the way could be that the bidding zones will be getting smaller and smaller, closer to the real physical nodes. But in my opinion, it's rather a longer way to get there.
Yes, but the problem then is you still have an abstraction between the physical representation of the system and the pipes and bubbles. Sorry, I'm using U.S. terminology. The pipes and bubbles representation, even if it gets more and more detailed, and you could say it goes all the way down to having every zone being a bus and a power flow network. You're still ignoring the power flow impacts that would add a lot to understanding the security of the system. So when you've gone down to that level, why not just go to nodal fully?
Yeah, but as I tried to explain, the results of this calculation, this PTDF matrix, it's actually input into this Euphemia algorithm. So every bit which is put into the common order book, it's evaluated according to impact of that bit to the flows over the grid elements. So it's part of that assessment already and part of that evaluation of the price. So it's like going there.
But you wouldn't need that assessment if you just went ahead and used nodal, right? You've done a layer of abstraction between the actual physical reality that creates an administrative process and errors that you continue to work on cleaning up, which is good. But why? Why not just go there directly and be done with it?
I would say it's really just about that you need some time to adopt or change the processes. And as I said, as it started really from really national perspective and no cross-country or international transfer at all, to have some simple representation of the border, to have multiple countries as regions. Now we are coming closer to the nodal. So I think it just takes time for all the involved to.
Yeah, there's definitely a big political element which you have to challenge with. So thank you.
We have a question from online.
Yes, Richard O'Neill.
Yeah, in the US, our market model is essentially solved by mixed integer programming, which is fairly well understood, and the software is publicly available for the most part. Could you explain a little bit about how Euphemia works?
Unfortunately, no, I'm not prepared for that.
Okay.
But if you just search for that, it's officially and publicly available description, so you should be able to find it.
Well, the public description doesn't really get you very far unless it's changed in the last several months. It's just basically most people who've looked at it don't understand how it functions.
Yeah, what I read, but it's already a few years back, was quite detailed documents. So maybe I could search for that again and share it.
Okay. Well, it's not your responsibility anyhow.
We have a question from the room. Please introduce yourself.
Yeah, this is Emilio Pinto from DRW. I have one follow-up question based on what Russ just asked. Some time ago, I was a little bit involved on the European market. One thing that was kind of growing was the regional coordinators, entities. How is those entities working right now, and what is how that fits on your on this environment?
Yeah, there are several regional security coordinators already in place. They are in full daily production operation. That was one of the points I mentioned at the beginning, that this is indeed a very interesting topic, very interesting cooperation. And it works. There are RSCs like TSC net in the region of Central Europe. There is Corizo in the Belgium, France, that area. There is Nordic RSC. There is RSC in the Greece serving for that region. And they have assigned, I think, 5 main processes they should coordinate. One of them is really a day ahead regional security assessment. So they do some coordinated security assessment with their participating TSOs. So they do gather some grid models. They do merge them together. They run some central calculations to assess whether there is some risk of some congestion or overload, and they also coordinate on possible remedial actions. It's very interesting topic, but I intentionally skip it because it could be for the whole presentation itself.
All right, final question from in the room.
So Prashant from Tesla. I'm curious to know, like, are you seeing inertia market coming in Europe? Because I hear about it, but I don't know how far it is there. And is it specific to some countries, or is it about the Europe?
It is already discussed on, let's say, some work groups or conferences. It's not urgent issue right now, but as I understood from the statements of system operators, it will be an issue in few years from now. So they are starting to discuss it and starting to prepare for it. But so far, we still have a lot of nuclear power plant and coal power plants. So there is enough inertia in the grid so far.
All right, well, let's wrap up and thank Peter one more time.
Thank you.
And this concludes our session. Thank you all so much for joining us both in person and online. We will reconvene in this room at 12:30 for session WB2, excuse me. Again, we remind you to not bring any food or beverages other than water into this room after lunch break. And again, there are food options. There's the 3rd floor snack lounge, and you can go out to go either north or south on 1st Street to find something a little more substantial. But yeah, we'll see you back here at 12:30. Thank you. And feel free to leave your belongings here as you're going to lunch.
Ashley, this is Dick. I was calling you in reference to your message earlier today.
Hi, everyone.
I don't know if it's supposed to be like this or not, but there is no video or audio from the room.
To the current decision-making pipelines. And of course, this work wouldn't have been done alone. Can you please go to the next slide? If it's next slide, please. Okay, wonderful. Thank you so much. So I won't be able to do all this work alone, and there has been a huge team of experts, but the all key personalities are shown here. It's a joint effort between the Columbia University led by Daniel Beanstalk. Too much? Could you please go a slide back? Can you please go a slide back? Thank you. Thank you. So as I said, the effort is led by Daniel Beanstalk of Columbia University. Daniel is right there. We also have a team at Hopkins, that is me and Jeru Liang. And we have a team at University of Arizona led by Michael Chertkov and Robert Ferrando, who is also right here. And other people contributed to different pieces of this effort as well. But the core to point out here is that our team is trying to work in this problem space using a very broad expertise. We have optimization experts, we have machine learning experts, we have experts in financial engineering and energy economics. And when you glue all of these expertises together, the real hitch here is to have software development expertise, which help you to move from individual components to the final product. And the effort is being generously funded by ARPA Perform. There were a few presentations earlier today in the morning from our colleagues within that program, but they were focusing on different issues. Really here, what we're trying to focus on is to understand how we can help improve efficiency, reliability, and loss of these routines that are used by ISOs using ML. And that is a prosaic form. The key understanding of us is what are the risks that arise in operations and what are the ways what are the decision steps that we need to take in order to mitigate those risks, even though in many cases we cannot exactly figure out what they are, simply because, for example, resources are not yet being deployed. And the key ingredient for success of our project is very close collaboration with ISO New England and New York ISO. These are not our project partners, but they serve an advisory role to us, and they provide critical feedback on every development and every ad that we're trying to develop. I saw a little bit earlier today Ginny Zhao from ISO New England, so she doesn't seem to be here, but she is one of the people we met at ISO New England to discuss that. Can we please go to the next slide? I don't see anybody at New York ISO here. Oh, you're there. Nice. Can we please go to the next slide? Okay, so here's a very quick overview of what our project has. And essentially, we broke down the methods that we developed for risk management using machine learning into 3 blocks. The core engine, which is shown here in the orange. Can we please go back 1 slide? Thank you. The core engine that we have here, it's in orange. And the idea here is that these are well-established tools such as SCAC, ROC, SCAD, which we try to emulate with a great detail onto how those tools are being used in the current practice. And we're trying to enhance them by using data analytics to produce what would be viewed as a stress scenario where an adversarial operating conditions are presented. And these adversarial conditions can be done with respect to both load and renewable generations. And we have real-time simulator, basically a tool that helps us to map scenarios into power system dispatch very quickly at a very high scale. This is the core decision routines which are being made by both the systems and the market participants, whether they're physical or they're traders. And in the following, we basically put out on 2 tracks. The green track is basically the blocks which are specific for ISOs. We want to understand what the cost and LMP risks are and how that would project into the mitigation strategies that ISO could take to, for example, improve reliability or reduce the cost. And there is a huge set of applications which are trader specific. And we focus here essentially on LMP prediction to devise smart strategies to be aware of risks that they're exposed to in the electricity market or how they can profit from these risks. And another chunk of this project is to devise new financial instruments that will help us to monetize this risk-adjusted behavior in the strategies. When you put these components together, they all fit in information into the visualization part of the project, which has the goal of basically map the results of our processing into forms where this information can be easily consumed and processed by decision makers. Next slide, please. So if we look at a typical decision-making pipeline, it's pretty well established. And if we look at the realism of the current industry, it's pretty efficient, right? They can solve optimization problems, SCAC, SCAD, taxonomy varies a little bit from one ISO to another quite efficiently. Can we go back to the previous slide, please? Thank you. The idea here is that if you want to bring machine learning into this, you need to be smart about thinking what extra value this complexity will introduce. And essentially, if you think about suitable roles for machine learning into the current decision-making routine, they're going to be essentially 3 procedures where machine learning is quite well. First one is related to the feature extraction and scenario generation. These are very well-established procedures for machine learning use. And for example, financial engineering sector, which is an inspiration for the Perform program, is one where those techniques are used profoundly. And the other one is going to be accelerated computations, where there is a lot of effort in our community to move the needle on these computations. However, along with that, there is a number of concerns. Typically, do we have enough data? How we can guarantee solution accuracy? Who will use it? How to convince industry to adopt those tools? And we're trying to answer this question in our project. Next slide, please. So essentially, if you think about that, these capabilities and questions can be organized in a very neat sequence of actions related to understanding what kind of features can be extracted from the data which is available to us from system operations. And in this particular setup, it matters because we have a lot more data than features that are critical for operations. Then based on these features, which we realize how critical they are, we can generate scenarios which are going to be representative of what stresses could arise. And if we enable to achieve very fast computations with machine learning, then we can really enable fast risk analysis over M number of scenarios, where M is an arbitrarily large number. The point that I would like to make that all of the steps, they don't mean to bypass or eliminate the traditional SCAC. In fact, this information could be integrated and fed into the SCAC using the monogram constraints. So we're not trying to abandon the current practice. We're just creating a parallel track that could be used either for supervisory action or could provide some input for the current routine. Next slide, please. So going about the data issues, it's important to know that data problems are not going to go away. And here is an example. Here I see that I'm using an example here, the development of offshore wind power plant. And frankly speaking, in this particular configuration, we already right now need to run analysis for both resource adequacy and for tentative operational planning on what impacts there would be. We don't have data, we only have meteorological data. We have very difficult access to wind turbine curves, which are proprietary. You can figure out, for example, which wind turbines are going to be installed in Empire Wind 1 and Empire Wind 2. There are press releases online, but you can never see what the wind curve would be. So data problems should not be an obstacle to adopt ML because there will always be data problems. So you have to adapt to work in an environment where some data is not available. And that is a drawback which machine learning can help us address by invoking scenario generation. Next slide, please. One more, please. And the flag means to signify that this problem is not unique to New York ISO. This problem is going to arise all over the country, especially when the West Coast will join the effort and start building, for example, offshore. The important thing is that even with meteorological data we have, and for example, we use NREL dataset here with 26 features, we can really figure out which one of those for existing applications can be viewed as a stressors. That is the influential impact factors that could basically help us to rot off. We engage into the principal component analysis, which is a fairly well-established data science technique that help us to understand what are the key stressors or principal components that will affect variability in this particular setup of wind speed and thus of wind power. And basically what we were able to see is that basically three components are typically enough to represent this time series information. The reason why three components is enough, it's actually very coalescent with the wisdom in financial engineering and in other cases where this technique is used for essentially dimensionality reduction. And that's effectively what we're doing. We are reducing a set of 26-dimensional space into something a little bit more manageable and representable. Next slide, please. So that is not all what we can do. We can use features and labels produced by principal component analysis, and we can now engage into an exercise of creating artificial data. The way how this artificial data can help processing is that while individual scenarios, they're not going to be real, because they inherit information from the principal component analysis, they're going to be realistic. And realistic, I mean, they're going to be close to reality. We don't mean to replicate reality with an individual scenario. It's pretty much guaranteed that individual scenario is going to be off. What we're trying to engage into here is a repeated scenario generation effort that is going to help us to represent the adversarial space that the system operator will face. So we're going to generate a large number of scenarios. Each scenario will be wrong, but taken together, they will shape the feasible space where we want to work with. And another important feature here and innovation is that not only we use GANs, which is a pretty standard machine learning technique for scenario generation, we informed it with information about the OPF. So we are not looking for statistically severe scenarios, which, for example, will lead to large errors. We're looking into scenarios which are going to be costly or difficult to operate system under. And that's why our integration between the two components, statistical error and severity of operations, which can be measured in terms of the cost or in terms of constraint violation, is an effective way to help us select those scenarios which are really going to represent operational issues, not statistical issues. Next slide, please. And a lot of things in the training process that we introduce in order to integrate the optimal power flow, the model that we use to represent power system operations in the training procedure. And the guess is that there is a lot of physical meaning. For example, we were able to show that the resulting sensitivity of the adversarial learning is going to be proportional to the locational marginal prices, to the unity factor of error, and to the maximum error that you're going to be observed in the day-ahead schedule. These are not the tuning parameters to our training procedure, but these are the outcomes of the training procedures that help us exteriori to define what is the meaning of each scenario and connect the scenario that we produce, which we deem to be adversarial, to particular actions that the system operator would do. Next slide, please. So here's an example of offshore wind power scenarios that we're producing for different days. We selected these days based on needing to represent different seasons and to have different conditions. And you can see that the ranges of scenarios that we capture is extremely plot. But if you go to the next slide, please. You will see that these scenarios are obtained by generating the error, and the key component here is to trade off between the statistical error and the severity of the error that is being observed. So these are two training objective function components that we use in our GAN training are being weighted against one another using a user-defined parameter K. And what you can see here that when we're becoming extremely conservative, then the adversarial error that we need to add to the profile becomes a flat blue line. And this blue black lines basically means that from this offshore facility in this particular zone, you're not going to have any output. That in this particular setup, what will happen is an equivalent of n-1 contingency. You have a flat line and there is no outcome during the course of the day. So in this particular set, training this kind of GAN network is very intuitive and could be explained in its worst case to the current practice. And what you achieve by trading off the statistical and worst case objective obtained through the OPF is really the degree of tolerance to taking risk that you as a decision maker can take. Next slide, please. So in this particular setup, the next part, which is important here, is a comparison. And we basically compare it and benchmark it against the current practice when we use adversarial scenarios versus robust reserve settings, where robustness was measured as a function of the day-ahead forecast. It's consistent with like a typical 5+7 rule used in California ISO, or 3+5 rules, which was originally devised through statistical analysis in the NREL report. And the idea here is that by helping analyze the trade-offs, we were able to achieve best economic performance using both the scenario generation and the fast day-ahead scheduling tools that we're using. Next slide, please. However, now what we have an ability to extract features from data, which matters for the system operations, and we can actuate these features in order to generate a lot of scenarios. What we also need an ability to process and analyze the scenarios at a very large scale. The number of scenarios is very large and we need to solve them very quickly. There are two parallel tracks that we're pursuing in this project. One is related to PINs, which is a physics-informed neural networks. And basically the idea here is to combine the computational power of neural networks with accuracy that physical models provide. And in this case, we face two problems. We need to make sure that whatever we get is feasible, and primarily we care here about the feasibility of the power flows. And we need to make sure that whatever machine learned results we produce, they're gonna be having both the physical meaning and have meaningful economic interpretations. For example, if we predict locational marginal prices, which is important for the trader side of our applications, that really we want to make sure that the primal solution we learn will have a meaningful connected dual solution so that the shadow pricing theory works. One of the features that we exploited is based on the fact that only a few constraints are actually binding. That concerns both the network limits and the dispatch limits. And we can exploit this because as soon as you have an inequality optimization problem with determined binding constraints, you can throw out all inequalities which are not let. And in this particular case, we essentially achieve a speed up by means of converting the original problem into a dense problem. The key is how to learn it. And as I'm going to show in my next slide, please, we have different types of constraints which are extremely different in their physical nature, and often they're not very well correlated. There could be a large number of constraints which are binding, which vary for roughly 1/3 or so. So in this particular setup, we're trying to also bound the error of learning so that the prediction we make on which lines are binding or not, it does not propagate into the decision error downstream. Next slide, please. So the procedure is fairly straightforward. We have a neural network that maps a vector of loads else into the vectors of binary variables, which tells us upwards and downwards constraints being limited. We have a fairly standard logistic regression loss functions, and we use this to train the neural network, which predicts which line constraints are binding. After that, we fed this information into our optimization problem, and we have an inequality problem turned into equality problem. And after that, we can solve a system of linear equations. The beauty of this approach is that the learning part in the first step, it could incur a bounded error. But the second step is that whatever solution you fix, it's being solved exactly. So both the outcomes, primal variables and dual variables, will have physical and connected economic interpretation. And at the same time, they're going to be guarantee on both feasibility and performance. Next, please. We also have a parallel effort, which is optimization based, and we aim for it to work into the real-time simulations. The idea here is that by improving sleep, wake, work, sleep cycle, we achieve an unprecedented level of CPU efficiency. And that allows, along with, like, of course, tuning of every job, it allows to solve about 1,000 real-time scenarios per second, which, if we couple with realistic data generation, is sufficient to analyze and explore through random walks a pretty large feasibility set of adversarial scenarios. Next slide, please. So here is an example to show how our machine learning works. And we tested it for New York ISO system, which has 1,813 buses and different levels of noise. We modeled onshore and offshore wind. And as you can see here, both the prediction in terms of LMP and dispatch are sufficiently strong. The error that we observe is fairly small, and on the scale of commercial application would not represent the difference. Also keep in mind that this result that I'm showing, these are not machine learned results alone. These are results that solving the step 2 optimization gives you, which is in turn informed by machine learning input. Next slide, please. So another important part is that when you have a very fast tool for performing computations and you have a lot of data generation, it's very critical to have the capabilities to visualize this data. And we have a dashboard, which is Python-based, and it works in real time and very effective in visualizing the thing. So we basically show which line congested, we show risks on elements, we show LMP exposure, we show predictions, we show corrective action that needs to be taken in order to reduce upcoming risks. We show distribution of LMPs, we show distribution of expectation of distribution of constraint violations, whether it's generation, dispatch, or long. We also have capability to introduce different risk markers, for example, Sharpe ratio, and so on and so forth. Next slide, please. So the concluding thoughts of this presentation is that using machine learning, we can really enable risk management and risk analysis on realistically large power system instances. And we can really find a decision-making pipeline and routine that help us to integrate machine learning strengths into the current decision-making pipeline of the current markets and do something which is currently with the current routine is not available. Next slide, please. So essentially, the success ingredient here is to think about machine learning, not in terms of the methodology, but in terms of the features that is being performed, operations being performed by the system operators and traders. If you think about it as feature selection, scenario generation, and risk analysis, then in this case, there are very natural roles for machine learning to fill in. And after that, I would like to finish. I probably am out of time, right? No, I'm done. Sorry. Am I out of time or am I on?
We have time for Q&A. You have plenty of time.
Okay, good.
So thank you, Yuri.
Thank you
for a great presentation. We are going to move to the Q&A section. And I just wanted to remind all of our online attendees that you can type your questions into the chat or raise your hand and we'll go ahead and call on you. Are there any questions in the room?
Russ Forward, Polaris. Sorry, I always have a question if no one else does. Yuri, interesting talk. I was wondering if you could help us get a clear view of when machine learning is appropriate and when it's not, because that was kind of, people like to think machine learning is a panacea for lots of things. And I'll try to stimulate an answer to that question by asking a question. Why use machine learning when you can directly use original data?
Again, sorry.
Why use machine learning when you can directly use original data? Because machine learning has to learn from something, right? And for some of the questions that you're looking at, you could take that original source data, and instead of applying this intermediate step of learning from that data, you could potentially use that data directly to get the answer that you're trying to get.
So the key answer to this is that it's very rare when machine learning is online. So this intermediate step that we introduced in locked, it can be done offline. So you push off computational intensive computations offline, and that provides you an opportunity to use the original data that you have in real-time operations when your decision span is very limited. You can say that you can extract a lot of information from available data set in real time. There is no doubt about that. It's just going to take you longer. If you can push off either GAN generation or PCA analysis offline, it saves you a lot of time. And the same goes for optimization versus machine learning used for computations. A lot of machine learning computations, the computational gain comes in real time because there is time invested into training this network offline. So the main, I would say, use for that is when you have a lot of information, a lot of processing that can be pushed offline. We're not trying to run here dynamic system analysis or evaluate transient stability of the system where a lot of real-time information is needed. We're trying to extract data, extract features from, I would describe them as historical data sets. And that is something which is naturally suited for offline operations rather than online. And then in online, you can use your either neural network or the principal component, or you can use the same original data set, which is going to be much smaller because you already know what the principal components are.
Yeah, and I would agree with that. I think if I were to distill what you said, the important point there is that you can use machine learning to help you get answers when you need them quickly, because to develop them without machine learning would take a lot more time than you have. And so and this is something that actually traders do quite frequently, is they'll take day ahead models and other longer term data and put into machine learning so that they can have instantaneous trading decisions to support their desks. So that's an example of what you're describing. Same thing would be potentially for real-time operations in utilities and markets, which is good. So that would be a bright line. Are there other areas that you think machine learning makes sense?
Pretty much where traditional tools cannot do the job. Like how else would you generate scenarios for offshore wind right now?
Okay, so now you stepped into my trap.
Not a trap. It's like a perfectly valid opinion. Actually, just the other day, I talked to atmospheric scientists about this topic. It was slightly different discussion, not perform related, but it was about understanding the effects of atmospheric boundary layers, which are very important for offshore wind. And there is simply nothing else you can do there without machine learning. Slightly different machine learning that we presented, for example, model reduction or related to the understanding regional weather patterns and prominence. That would be one of those. There is a lot of effort that where machine learning could serve as a bridge between.
Well, let's stick with that. You can because I think you are now running into a problem because you're using machine learning to distill information and expand upon it. And if we think about machine learning, it's nothing more than a glorified regression methodology, right? And there's a problem of overfitting that you can get into. And so unless you're expanding the information space that you have to operate on, you run a real risk that your machine learning is really corrupting the goal that you have for getting answers. And so unless you're bringing in other information that goes way beyond what you can do with other methods, you need to be cautious about that. And so specifically for like offshore wind forecasting, if you're not bringing in more fundamentals into the weather forecasting process, for example, maybe using climatological models, not climatological, but the large scale numerical models that are continuously being developed, and you're not driving from those fundamentals, then machine learning is going to learn the wrong things because of overfitting.
I still don't see a trap. Could you please clarify it?
I'm sorry, say again?
I still don't see a trap. Could you please clarify it?
Well,
You said you said a trap. I just don't see it.
The problem with machine learning is that people can apply it to create data that doesn't really exist.
I think
like your
Daniel
scenario
has
generation
something
process.
to say.
At first blush, machine learning or deep learning in our case is just a one predictive methodology. It doesn't have to be the sole methodology. It doesn't have to be the only methodology that you deploy in real time. You can use both. But the deeper point in the context, I mean, it's not necessarily the case that I love deep learning. You know, deep learning could put many of us out of work. But that the training process can leverage those mathematical models that you described. This is and especially together with GANs. So you end up making better predictions than the very technical models. That has been the experience in other areas where machine learning has been deployed and won. So yes, I totally agree. Let's use those very fundamentally based models, which are very complex and very difficult to interpret. In fact, the weather people themselves have trouble interpreting the different models. They conflict each other and so on. But deep learning can use the output of such models to perhaps make better predictions.
Sorry for interrupting. I also think Mihai wanted to
Sure,
say something on
it
this
can
topic right
create
behind Daniel.
bad data, but you know, this gets applied, it gets used, people learn from the mistakes, and they move on.
Because I think it was just related to machine learning, right, Mihai?
Yeah, so I'm going to add to the controversy, as you know me. First of all, thank you, Russ, because machine learning is overused by a factor of 10, but I'm not sure it's the case here. So here's an example, right? So, I mean, in the end, it's a big regression machine. That's what machine learning is. It's a gigantic regression. I mean, in reality, it'll be hard for you to specify a regression model to forecast, boundary layer in a place you never have data before, but you have neighboring data. How are you going to do that? You see my point? So I think it does have a use when it's data driven. When it's simulation driven, we replace simulation, it's a bit of a different argument. So that there the issue is a bit more tenuous, I would say. But certainly, but you mentioned the boundary layer. For the boundary layer, I think absolutely you have to do regression, and it's very hard to posit the model. You might as well do ML.
And just to comment on that, there are also composite models where you use a combination of the simulation and probes, realistic probes. It's used, for example, very often in climate science when they cannot take measurements everywhere. They take measurements in partial locations, right? And they then expand it using simulations to make more generalized, more continuous granularity models. And these models, they've been used to make trillion-dollar policies. If climate scientists convince decision makers that they have reliable enough machine learning models, which are physics-based, which is based on real observations and use some simulated data, there is no argument not to convince this organization, FERC, to push ISOs to use machine learning in a similar fashion. After all, the power sector is far less costlier than multi-trillion decisions that are being made to combat climate change, right? We wouldn't say, I hope, that climate scientists make up data, right?
So we have one question online, and I'm sorry to cut this off, but we're already a little behind schedule. So Brian Park, please, I have given you the opportunity to unmute yourself. Please ask your question. Brian Park, would you like to ask a question? Okay, so go ahead. Yeah, let's thank Yuri one more time.
Thank you so much, Yuri. We appreciate a good debate. But next we're going to have Dr. Lee Wu and it's a PhD? Oh, PhD candidate Chun Bong Chen. And they're going to be virtually presenting on boosting power system operation economics via closed loop, predict, and optimize. And they are from the Stevens Institute of Technology.
Hi, is everything okay? Can you hear me clearly?
Yes, we can hear you.
Okay. Hi, everyone. I'm Shenbang Chen from Stevens. It's my pleasure to present my work with Professor Lee Wu, which is boosting power system operation economics via closed loop, predict, and optimize. This presentation includes 4 parts. First, I will briefly introduce the background and the engineering problem. And then I will introduce 2 approaches we designed for this problem. Finally, I will summarize the whole presentation. Okay, let's move to the first part. We focus on the general operation problem from an operator's perspective, which is in this open loop, predict, and optimize framework. First, the reserve requirement and the energy availability are predicted. And then the operators will use these predictions as inputs to optimize the day-ahead operation plans. Finally, after getting the actual energy availability in the real-time stage, the operators will adjust the day-ahead operation plans optimally. And the operator's goal is to achieve the minimum system operation cost. And let's specify this process using some mathematical models. First, after getting the predictions in the day-ahead stage, which are the W hat and R hat here, the operators will solve this day-ahead unit commitment problem to design the on-off stay and base point generation and the reserve deployment of the units. After that, getting the actual energy availability in the real-time stage, which is the W tab here, the operators will solve this real-time economic dispatch program to design the on-off state of the kickstart units and generation and adjustment and the reserve usage. Finally, after solving these problems, the actual operation cost is available, and a lower operation cost indicates a better operation economics in this presentation. Even though the OPO makes sense, we found it has 2 flaws. First, the reserve requirement is always redundant, because they are generally decided by the rule of thumb. Second, which is also the most important, is that its predictors simply pursue a prediction that is more accurate. However, a more accurate prediction may not enable a better operation economics. And the second point here sounds a little bit counterintuitive. So we plot this figure, which shows the relationship between the prediction error and the economic loss. And this is the equation to calculate the economic loss, which measures the gap between the operation cost based on the prediction with some error and the prediction that is error-free. Here, if we compare the point A with the point B, we can see that even though the points have the same MAPE as 6.5%, they enable different economic losses. And if we compare the point B and the point C here, we can see that the point C has a worse prediction error, but point C can still enable a lower economic loss. This is because the power systems are very complex and nonlinear. So the relationship between the operation cost and the prediction error is asymmetrical. And this red fitting line shows this asymmetrical relationship clearly. So we quote the sentences from Yashir Bengil. In many real-world applications, the ultimate goal is not to make good predictions, but rather to use the often noise predictions to make good decisions. And in our case of power system operation, we believe that the energy prediction should consider the operation goal so that the operators can achieve a better operation economics. And we call this idea closed loop, predict, and optimize. And based on this simple idea, we present an approach called feature-driven SIPO. To better understand the SIPO, we compared it with the OPO we just mentioned, and we highlight the differences with red color. Here, the OPO on the left uses the accuracy criterion to train the predictor and doesn't care about its impact on the optimization. So we say it's open loop and accuracy oriented. But our SIPO on the right trains the predictor using a cost criterion. This is achieved by feeding the operation cost back to the training stage and evaluating the prediction quality by whether this prediction can enable a low operation cost. So we say SIPO is closed loop and cost oriented. And we should also notice that the SIPO, the OPO, needs to do the prediction and the optimization one by one. So it's predict then optimize. But this SIPO can do the prediction and optimization in one shot. So it's predict and optimize. And the SIPO needs 3 modules. The first module is the data processing module, which will do the feature selection and training scenario selection. And then this module, which is the modeling and training module, will model a cost-oriented empirical risk minimization problem, and then solve it to get a well-trained predictor. Finally, the last module will embed the predictor into the unit commitment problem. And the predictors can use, then the operators can use this new model to do the prediction and optimizations in one shot. And here we highlight the second module because it's the most important part in the whole framework. So let's look at this module closer. The core of this module is a loss function called SPO. This SPO loss function measures the gap between the imperfect UC cost and the perfect UC cost. And then it forms an empirical risk minimization problem based on this loss function. This problem is to train a predictor matrix H with the objective to minimize the in-sample SPO loss. And the product of the matrix H and the feature vector F equals the energy predictions. So this is basically a linear regression problem. And its intractability comes from the fact that all the training scenarios are coupled by this predictor matrix H. So the whole problem is a large mixed integer programming problem. In fact, we can solve this problem directly using commercial solver like Ruby, but it definitely will be very slow. So we customize a Lagrangian algorithm to solve this problem in parallel. And after solving this EIM problem, we can get a well-trained cost-oriented predictor edge that is tailored for the operations, which will be embedded into the unit commitment model to get a prescriptive model. Now, let's compare the original using model and the prescriptive using model. The original model on the left needs the prediction before the optimization. And the predictions are accuracy oriented. On the right-hand side, the SIPO is able to do the prediction and optimization in one shot because it's directly driven by the features. We say this is prescription process because this prescriptive model directly makes decisions according to the feature data instead of simply decision or prediction. Now let's take a look at SIPO's performance on the operation economics. Here, we use the accuracy-oriented predictions from a Belgian ISO as benchmark, and we use 1 year long data set to do the out-of-sample testing. And we configure 7 different SIPOs with different training scenarios. In this figure, the blue upper bound here is the benchmark OPO, which uses the accuracy-oriented predictions. And the blue lower bound here is the perfect then optimized method using the error-free predictions. And the red curve between them is our SIPOs. As we can see, the SIPOs can outperform the benchmark OPO with 1% at least and 4% at most, which means that all the SIPOs can effectively lower down the operation cost in this case. And considering the benchmark prediction are industry level and high quality, we believe that this improvement should be well respected. Okay, now let's take a look at the prediction accuracy using 4 commonly used criteria. According to the red columns in this table, we notice that the cost-oriented predictions are slightly worse in MAE and RMSE, which means that these predictions are less accurate. And we also notice that this prediction, which is cost-oriented, have a lower MOPE and a higher MUPE, which means that they are generally conservative and lower down the actual realization. This is because the closed-loop learning enable the predictors to learn that a prediction that is overestimated may trigger the expensive quick-start units. So they prefer to be predicted slightly. Finally, let's test the Lagrangian algorithm on a large size system. The 2 columns on the left compare the training time, and the first column trains the predictor using GRUB directly, while the second column trains the predictor using the Lagrangian algorithm. As compared, we can see that the Lagrangian algorithm enables a 42% acceleration in training time in this case, and the remaining 2 columns compare their optimality. And we can see that the Lagrangian algorithm doesn't lose much optimality. Its gap is still less than 1%. So we believe that the SIPO with Lagrangian algorithm has the potential for the large size system in the real world. Okay, now we already saw that the feature-driven SIPO performs pretty well. So we are thinking about how to make it better. Motivated by this thinking, we upgraded the feature-driven SIPO to a bi-level SIPO, which is our second approach. Let's compare the feature-driven version with the bi-level version using this figure. Again, we highlight the differences as red color. We can see that the feature-driven SIPO only fits back the day-ahead operation cost, and its reserve requirement is still based on the rule of thumb. On the other hand, the bi-level SIPO fits both the day-ahead and real-time cost back and jointly tailor the energy prediction and the reserve requirement. And in addition to these 2 points, we also want to emphasize that their empirical risk minimization structures are quite different. In this single level feature SIPO, its ERM structure is single level, but the upgraded version uses a bi-level structure. This is very helpful, and we want to demonstrate this by comparing their mathematical models. We can see in this slide, the single level ERM packs the predictor training and the in-sample operations into this single level model. So the training and the operations have to share the same objective, and this may cause in-sample operations fail to follow the least cost principle because the operation in this model just want to minimize the SPO loss, but it should minimize the operation cost in the practice. As a result, the in-sample operations X could be compromised and the predictor H could be overfitting. And on the other hand, the bilevel structure allows the training and the in-sample operations to use their own objectives. As we can see, this ERM problem has one upper level and two lower levels. And the upper level is to train the predictor metrics H and R with the objective to minimize the total operation cost. And then the predictions W hat and R hat will be given to the first lower level, which is to mimic the data hat operations. And after that, the data hat decisions X will be given to the next lower level, which is to mimic the real-time operations. And after solving these two lower level problems, the operation plans X and Y will be fed back to the upper level for evaluating the prediction quality. And this ERM problem can ensure the in-sample operations X and Y to always follow the least cost principle, which align with the practical operations. And this will be very helpful in avoiding the overfitting predictors when the scenarios are very few. Okay, next, we compare the SIPO with the famous two-stage stochastic programming in terms of the operation cost on 4 representative days. The blue line here represents the operation cost based on the stochastic method using different sizes of scenarios from 1 to 99. And the red line here represents the cost based on the bilevel SIPO with different sizes of training scenarios from 1 to 7. First, we can see that the SIPO with 7 scenarios is very competitive to the stochastic method in these 4 days, in which the stochastic method has 99 scenarios. Moreover, we can also see that SIPO can perform much better than the stochastic method when the scenarios are very limited, and its performance curve is pretty stable. And this is contributed by the bilevel structure. Okay, that's all about the case study. And now let's summarize this presentation. We focus on the general operation problem in this open loop predict then optimize framework. And then we use an idea called closed loop predict and optimize to design 2 frameworks. The first one is the feature-driven SIPO, and the second one is the bilevel SIPO. And according to our case studies, we can get 3 points. First, the SIPO shows the potential in lowering down the operation cost by generating cost-oriented predictions that is tailored for the system operation. Second, a cost-oriented energy prediction may be slightly worse in the traditional accuracy perspective. And the last point is that the bilevel empirical risk minimization problem enables the SIPO to lower down the operation cost, even only use very few scenarios. Okay, last, we want to emphasize that SIPO is just an idea that we should think about the optimization goal when we are doing the prediction. And in this presentation, we use a linear regression method to achieve this idea. But it should be very interesting if we use more powerful methods like deep learning and reinforcement learning to do this in the future. And currently, we have 2 publications out of this idea, and we have put the source code on the GitHub. And you can scan this QR code to get them. Okay, that's all about the SIPO work. Please feel free to ask me any question. Thank you.
Okay, thank you, Xianbang.
Thank you.
Do we have any questions in the audience? And then another reminder, if you are an online attendee, please feel free to ask your question online. Anyone?
Hi there. Thank you for the presentation. I just have a small clarifying question. So as far as I understand, your framework is inspired by the work of Adam El-Mattoub, right? I didn't see a reference, but he has a very similar paper on this topic. And in his paper, he uses the taxonomy predict, then optimize. And I see that in your presentation, you use both predict, then optimize and predict and optimize. So I really wonder if there is if it's just a figure of speech or there is a meaningful change relative to Adam's work. Thank you.
Hi, that's a good one. That's a good question. Thank you. Yes, we are inspired by this paper you mentioned. I think the difference between our framework, in the original methodology paper, it's basically focused on a linear programming method, but we extend it to a mixed integer programming model. So that's the major differences.
But as far as I understand, you still use continuous regression, and you solve a MIP problem with a continuous regression, and he's solving, I believe, a convex program with continuous regression. I just don't have paper in front of my eyes right now. So what is exactly the innovation, how to integrate regression into the optimization model? Can you comment on that, please? Thank you.
Okay. So in the original methodology paper, they used the linear programming model so that they can do the dualization, which is make the training this empirical risk minimization problem easier. But in this problem, is a large mixed integer programming model. So we have to decompose it, or we will solve it very slowly. So I think that's an extension. But if you say it's the innovation, I think it's not strong enough. I agree with you on this point.
Your contribution is the decomposition. Do I understand correctly?
Yes.
Oh, thank you. Now it makes sense. Thank you.
Okay. Yeah. But we didn't discuss the solving methodology in this paper because it's time consuming. So we just present this model and its idea here in this presentation.
All right. Any more questions from the audience?
Yeah, I have a follow-up question related to decomposition. So you mentioned you use a Lagrangian method, right? Are you using the standard one? I mean, traditional one?
I think it's a customized one because I think the Lagrangian algorithm, it depends on the problem structure. So
yeah, because we know there are many difficulties related to standard or say traditional Lagrangian. So just wondering, are you making any changes to standard one?
I don't know the differences between the standard one and the traditional one. Could you?
Sorry, it's the same thing. I call it the same thing.
Okay, so I think the idea is basically the traditional one, but we customize the process in solving this problem.
So can you comment on how do you do that? Like you change the step size or you make changes to the coordination process?
No, the step size is I think it's the traditional one, but we need to analyze the structure and depends on which constraint to decompose. That's the customized point.
Okay, so you're not directly like a relaxed system level constraint, right?
No, we're not.
Okay, I see. Okay, yeah, thank you.
Thank you.
Okay, and then we do have one online question, so.
Yes, we have a question from Mahan Mansouri. You can unmute yourself and ask your question.
Hello, this is Mahan Mansouri from Pacific Gas and Electric. Could you hear me well?
Yes, thank you.
So one, it is correct that one of the advice's goal is to minimize the operation cost, but the main goal is reliability, right? So the main reason for the open loop prediction is that they do the prediction first to be able to predict the state of the system as close as possible to reality, to be able to maintain the reliability and then minimize the cost. Your method, the closed loop, I think if I understand correctly, is increase that error, and that has a reliability implication, right? While you might lowering the operation cost, but increasing might cause increase the reliability cost. So I'm wondering how you would address that, or because that, as I said, the main goal is of the system operator is not the reducing the operation cost, is maintaining the reliability. So if you could make a comment on that, I appreciate it. Thank you.
Sorry, I didn't hear you address what?
Reliability implication. As you increase the error, you might lowering the operation cost in the closed loop. But if the error is higher, it might increase the reliability, right? Because you basically the prediction, what you're predicting and optimizing is further away from reality if the error is higher. So that has a reliability implication. And that's something I want you, if you could comment on that and how you might be address that.
Okay. So this closed loop framework is not to replace the traditional open loop predict and optimize. Basically, it's tailor the role predictions to gather more specified, or that is tailored for the unit commitment or the system operation problem. So you can still gather accurate predictions in the original framework. I think that makes sense. It doesn't replace the traditional one. So I think the reliability is not exist. If we thinking about this is only an option instead of in charge of everything.
All right. Thank you.
Thank you.
Okay, thank you again. We're now going to be moving on to our second to last presentation, which will be the synergistic integration of machine learning and mathematical optimization for sub-hourly unit commitment by Jianghua Wu from University of Connecticut.
Yeah, hello everyone. It's my great pleasure to present our recent project here. Yeah, let's wait for the slides. So before that, our project is sponsored and collaborate with the MISO, and we have collaborated with MISO for several years. And today I'm gonna present our most recent result about this problem-solving algorithms. So today's topic is about the synergistic integration of machine learning and the mathematical optimization for sub-hourly unit commitment. Next slide, please. Yeah, so from yesterday and today's presentations, we have heard a lot of new challenges in the power system, increase the penetration of renewable resources, and also we didn't catch this topic. It's it's suggested to use the sub-hourly schedule to help increase the reliability and the flexibility of this unit commitment operation. And also we have heard about new challenges about incorporating about the combined cycle units and distributed energy resources. For many these new challenges, we have observed that there are computational challenges for these traditional unit commitment problems if we incorporate all these new challenges. Next slide, please. Yeah, so in our previous work, we have worked with MISO on their one problem. This problem has more than 1,000 generators and more than 15 1,000 virtual transactions. And the problem is modeling as a sub-hourly UC, and we use 15 minutes time as a time interval. And for that problem, when we test on the commercial solver Groovy, and it's used branching cut, we can find no quality solutions after even 20 minutes. So based on that problem, we developed a new decomposition and coordination approach, which based on Lagrangian relaxation, but not traditional one. So by using that algorithm, we found a near optimal solutions with 0.9% gap within 20 minutes, and as can be shown in this figure. And the figure you can see, we found like a 0.84% gap solutions even within 30 minutes, which is much faster than the Groovy did. And then how we can do that is like we have the key. We have the key to overcome the complexity issue for when we consider so many new challenges. It's about the decomposition and coordination. Next slide, please. Yeah, so for when we're talking about the decomposition and coordination, what came to our mind is like a Lagrangian relaxation. But we all know it's like a job did about like 20 years ago because of many major difficulties for the traditional version. For example, like it has significant computational effort, and it may have zigzagging in the Lagrangian multiplier convergence, many things like that. But it do have a key feature. It can reduce the complexity based on the decomposition process. Yeah, please go ahead. Yeah, so in our previous work, we have developed a new version of Lagrangian. We overcame these major difficulties. For this version, there's no need to solve all subproblems when we need to update the multipliers. We only need to solve one subproblem, and for this subproblem, we don't even need to like solve it to be optimal. We introduce a very simple convergence condition called a surrogate optimality condition. Once the single subproblem is solved to satisfy that condition, we move on to solve the next one. And at this process, we update multipliers. And based on this, we can find the near optimum solution with a guaranteed convergence. And based on this, we call such kind of subproblem solution is called good enough. And with this, we can have reduced the computational effort, and we have a smoother Lagrangian multiplier updating. Yeah, go ahead, please. Yeah, so after that, we have this latest version of Lagrangian. We incorporate with like a penalty term into this SALR. We call it SAVLR to accelerate the convergence by introducing a absolute penalty term. And then also we developed some like algorithm to like obtain the good enough solutions quickly, which is like based on the ordinal optimization concept. Like we modify solution based on some previous solutions or by solving some simplified models. Yeah, go ahead, please. Yeah, but even by using the latest version, we have solved the example I have already shown for the MISO problem. But if we consider more challenges, like if we have combined cycle units considered or many other challenges considered, then this SAVR we may still fail to solve the problem within the time limit. So what we can do to further improve that, like what came to our mind is whether machine learning can be helpful. Yeah, next slide, please. Yeah, so we have already seen many machine learning based approach for unit commitment now, and we divide them into two parts. And for current implementation, most of them are implemented for hourly unit commitment. And they are indirect ways like learning branching strategies, removing inactive constraints, or fix those stable binary variables. And also for the direct ways is like use those machine learning techniques to directly learn from the demand and to predict the UC solutions. But for all these implementations, when they consider new challenges, they must have some problems like it can be time consuming if they still need to call branch and cut, right? And if also they need to have difficulties of data preparation and the time required for training. So, and one more thing is like if they have faced like an unfamiliar case, which means the new case is not covered in their training data, what would happen and what they should do. So considering all of these, like we are thinking about what we can do besides this. We are thinking about like whether we can learn to learn for the, our SAVR subproblem solutions. Why we want to do that? One reason is that after decomposition, a subproblem solution is much easier to learn comparing to the original unit commitment if we consider all those challenges. And the second, subproblem solution, we don't need to be optimal, so we don't need to predict optimal solution. What we need is a solution satisfy that condition. So there's a big space we can have the mistake to predict. So next slide, please. Yeah, so very quickly go through some key equations here. Like the equation 1 present like a traditional UC formulation. In our consideration, we have already considered system demand, transmission, and unit level constraints. And the equation 2 presents how we do the SAVR framework. We relax the system demand constraints, but for transmission constraint, we use the soften constraints. We allowed erase like a slack variables and add a penalty to that slack variable. And we also have a penalty term for the violation of demand constraints. After this, then equation 3 is the thing I presented before, is the surrogate automatic condition, which is the key of this learning. We only need to learn a solution to satisfy this equation 3. And this is very simple. It's just like it need to be this surrogate due value need to be less than a certain value calculated by previous iterations value. Yeah, next slide, please. Yeah, so then we're considering how to learn this subproblem solution. Then we want to make it as simple as possible, since we don't need to like learn a very optimal solution. So we start from a very simple multi-layer perceptron model. We did some preliminary testing and it did good in hourly UC, but when we switched to sub-hourly UC, we found some problems with multi-layer perceptrons features, like it may need high computational efforts when training several multi-layer perceptrons, because in this model, we like require each subproblem have one multi-layer perceptron to do that. But when we need to train a lot of multi-layer perceptron, it requires a lot of time. And the second is like when switched to the sub-hourly UC, the time dependency is increased, and it's harder for the multi-layer perceptron to predict accurate prediction to satisfy the equation 3. And the third thing is multi-layer perceptron cannot guarantee the feasibility of those unit level constraints. So considering all this, we want to like develop something is generic model can predict different solutions for different subproblems, and we can also make the prediction is feasible and maintain a high success rate to satisfy equation 3. Next slide, please. Yeah, so this is like a model we developed. We call it a generic GRU-based model. In this model, we use like modeling the input output as a time-based sequence, and we also like borrow the idea of the machine translation. We use the padding process to do that, so we can like fix the whole input and output as a fixed length, and we can make the it able to predict solutions for different subproblems with different number of units. And second is we adopt this encoder-decoder structure, and within this structure we have the GRU and attention combined it in this structure, which is to like capture high dependency among the coupled theories in sub-hourly UC. Next slide, please. Yeah, and then we also have one rule-based feasibility layer. We call it a mask. We incorporate it's somehow like similar to the physical information embedded in neural networks idea. We have some correction process in this predicting process in the decoder block, and which fix the prediction during the predicting process. So we can not make sure, but we increase the feasibility rate to a very high level. And the last thing is we have talked about like if the other machine learning method can have a problem with the unfamiliar case, what they can do. So here we consider this because if this machine learning cannot provide a good enough subproblem solution we need, what we can do here is because we are under the Lagrangian structure, we don't need to worry about the original problem. But for that single subproblem, we can call branch and cut or some other heuristics to quickly fix these subproblem solutions. So we don't exactly rely on machine learning only. So we call it like a graceful degradation with some slightly increase of computational time. Next slide, please. Yeah, so here is a flowchart of how we solve the problem. But here, actually, what I want to show you is like we didn't change anything about the original flowchart. But the only thing is before we solve the subproblem, we have the prediction, and we will check the prediction whether it's feasible and satisfying the SOC. Then if it's good, then we directly apply that prediction to solve problem. And that's our key to speed up this subproblem solving process. Next slide, please. Yeah, so for this machine learning problem, we now only like test the IEEE 118 bus system during the time limit. And so here we have some testing results present here. We compared like using multi-layer perceptron, and we also embedded that a padding process for multi-layer perceptron, and also a GRU-based generic model. So here, from this figure, we can see the most upper line is the generic multi-layer perceptron. It shows like it means like it has no ability to predict solution for different subproblems. And for separate multi-layer perceptron, it can have the prediction, but it required a lot of training time. So, but we have a GRU-based model. It can then to predict solution for different subproblems, and it will be less effort for training. Next slide, please. Yeah, and then we test 100 new instances. We also set our both SLI and SAVR stopping criteria to be like a 40 major iterations, or like when the mid gap is less than 1% gap. So we compared those results here. And first of all, when we look at this table, we can see if we use the SLR with different models, when we use generic multi-layer perceptron or separate multi-layer perceptron, it can hard to guarantee the feasibility. Like it's almost like just 30% feasible predictions, and only 3% of them are good enough in this sub-RDUC. But when we apply the SAVR and the GRU-based model, here we increase the feasibility rate into 98%. And also we have a 43% are good enough to satisfy the SOC, which result in the following two figures. We have less iterations required in this solving process, like the light blue column and the dark blue column, they are like the iterations required for SAVR, but we can see SLI require 14 major iterations, but SAVR only need the 26 or 28 iterations to converge. And also in CPU time, because we needed less iterations and we have more iterations solved by machine learning, and we saved a lot of the computational time as the most dark blue line at the bottom here. Yeah, next slide, please. Yeah, here is the conclusion for this project is we are looking to like some hard, complicated unit commitment problem when facing new challenges. And we believe that decomposition coordination structure is a key to reduce complexity. And we integrate this decomposition coordination framework with machine learning together, and we hope this can help to solve the problem quickly and make sure those problems can be reliable to be solved. And we have a lot of belief this approach holds much promise in the future. Yeah, next slide, please. Yeah, and I think I will end here. That's all. Thank you. Any questions?
Thank you so much for that amazing presentation. Do we have any questions in the room? Great.
Hi, my name is Hao. I'm from Princeton, and your presentation is really good. I really enjoy your presentation. But I have one, I think maybe I misunderstand it when you say something. So my question is like when you are saying during the sub-hour problem, you are not looking for the optimal. So you're using machine learning to make it faster. I mean, in that sense, can I think in a different way, say, since you are not looking for optimal, you just want to find a feasible solution or satisfy or some solution that's satisfying the constraints. Can I use like say DC power flow model, or can I use like can I reduce some constraints or variables to make it easier to solve?
Yeah, so the problem here is like why we say we don't look for an optimal solution is that we want to make sure the algorithm can converge. And if we satisfy that surrogate optimality condition, then we can make sure the algorithm will converge. So we say it's not, we don't need optimal solution to converge, but we only need a good enough solution to converge. But it's not like to reduce the feasibility or like optimality for the original model.
Yeah, I think there's a confusion here. I think what you ask is to the overall problem, right? Yes, when we're talking about it to the sub problem.
Yeah.
So at the end, we still use heuristics based on subproblem solutions and to find the overall solution. So when we solve the overall problem, we still satisfy all constraints. Yeah. Okay.
Anyone else in the room? Great.
Hi, I'm Shubo from the New York ISO. Just a quick question about uncertainty. So like you said that you use machine learning to generate a set of like feasible solutions, trying to give a warm start to the Lagrangian relaxation as a problems. So like when you do the training for the machine learning, do you consider like topology changes or like a system conditions, like, you know, generation outage or renewable uncertainties, anything like in the...
Yeah, thanks for the question. For our current implementation, we haven't considered like uncertainty or like a topology changes. Those things that we haven't considered that. For our consideration, we have already like considered like something like a system initial condition change, or like for example, a unit initial condition will be different for every day. So we already considered such kind of things. But for those many things like uncertainty or like so some unit may be dropped. For those things, we haven't considered all of them because it's like a step-by-step process of maybe those things need to be considered in the real market implementation, but in our current implementation, we only consider initial unit conditions. Yeah.
I think it may be a follow-up to his question. When you're talking about your 500K training case and 100K test case, can you give us a little more information, like what are they, since you are saying you are not considering those contingencies?
Yeah, okay, thanks for the question. So for our current like training and testing, they are like we are varying the system demand and we varying the unit initial conditions. For those things like we have the like a fixed system, but we have the loads information are changed. So like loads are the changed information, and we use branching cut to solve. We use SAVR to solve the problem, but during this process we use branching cut to solve our subproblems. So we have the loads subproblem solutions as our target to learn.
All right, anybody else? Okay, thank you.
Yep, thank you.
All right, we're going to move on to our last presentation before break, and that's going to be by Dr. Vladimir Dvorkin. You may recognize this last name. But this presentation is on privacy, preserving synthetic dataset generation for power systems research. So take it away.
Yeah, thank you. Thank you so much for this kind introduction. And it's a great to present my work in front of you today. So you have a very beautiful room there. I wish I was there, but Delta Airlines had a different plan on me. So anyways, a lot of speakers today, they show the importance of having credible data for simulations, enabling machine learning application, power systems, but generally for decision making. In this work, we're trying to answer the question, how do we source this data? And when we think of a role of data in power systems, and we ask people where data should belong to or where it's belong, it depends where you ask. In Northern America, the prevailing argument that the data must be private, so that the entity that's holding this data can enjoy its privacy and cybersecurity against informed cyber attacks. There are also a lot of regulations that require us to keep data safe, but also having exclusive access to data brings competitive advantage. When we go to Europe, we see more argument that, okay, data can be seen as a public good. It's indeed improve decision-making in the industry. It removes barriers for entry for new business models centered around data. But also for researchers, it allows for new innovations and boosting research. Here in North America, so private data, prevailing arguments towards private data, and when you're working at Energy Initiative of MIT as a postdoc, typical conversation with a data owner would look something like that. The companies comes with a challenge, they ask us to do some planning optimization for them, and we get very excited about this optimization. We can do it, but we ask them for data. We ask for cost structure, we ask for generation time series, we ask for their budget limits, and this is at this point they become extremely hesitant and they try to abstract all this information, and we end up working with some synthetic data. So it looks like it's very difficult to get access to real data, and the question is, can we enjoy synthetic data instead? Can we solve the same task using synthetic data? When we see where other communities are going to, so if nowadays majority of AI models are trained on the real data, such as ChatGPT that uses data from web left by real users, so in the future, the prevailing source of data will be synthetic information that will be obtained based on the results that ChatGPT already spits out currently. And it's very interesting perspective and vision for the role of data in the future. But in power systems, we already have a lot of examples of synthetic data sets. So we have a synthetic data sets from Texas A&M repository. We have PIPESAR, synthetic data for entire Europe, recently introduced a synthetic data repository for national electricity market of Australia. And we already we have standard IEEE benchmarks, so on and so forth. We already have a lot of synthetic data to work with, and it's extremely helpful for us as researchers to develop new models for optimization, machine learning. The problem with these synthetic data sets currently is that they often come with the following statements: that the data bears no relation to the actual grid, that the test case is fictitious, represent fictitious transmission, and it doesn't model the actual grid. So, and this is a problem with currently with synthetic data sets, that it's only abstraction of the system. So, to resolve this challenge, we adopt solutions from algorithmic privacy to generate synthetic power system data sets from real world data sets. And in a nutshell, our approach looks something like this. We have a real world data set, and we add noise to this data in order to produce its privacy preserving counterpart. And then, okay, this is a privacy-preserving version of a data set, but it lost a lot of important features of the real data. So we use optimization-based post-processing in order to restore important features of the data, like preserve the trends in this data, but also enable privacy at the same time. And we see this pipeline as a very powerful mechanism to release real-world data sets in a privacy-preserving way. And first, we need to formalize privacy. So we think of a universe of data sets, like different realizations of loads, right? And we have realizations of data sets from this universe, and we're interested in protecting differences between data sets. And if we use any data set in computation, we would like to guarantee that data sets that are within some neighborhood one from another will be indistinguishable in our simulations. And this is a goal of privacy, not to allow adversarial mapping, not to allow to reverse engineer the solution, data sets from the solution that we release. And we can achieve this goal using a rigorous framework of epsilon differential privacy. So it's a bit abstract framework, but it works in a way that it randomizes the computation of interest in order to obfuscate data sets that you use in your computation. And the idea is that, okay, you take two different data sets in your computation, and through the results of this computation, you can differentiate between data sets. The outcomes are different. But when you randomize your computation, you make the outcome statistically similar. You can think of data sets D and D prime and answers in these data sets. And you can differentiate between data sets. But the moment you add a noise to this computation, your response will follow some probability distribution. And when you observe the sample from this distribution X hat, you cannot tell from which distribution came from. The one used in data sets D or D prime. Hence, you cannot differentiate between data sets. And epsilon is a control parameter. The smaller the epsilon, the smaller privacy loss is induced, and the more protection you provide to a data set. But okay, it's a bit of a theory. It's a bit of abstract concept. So, and here is an illustration how we can reason about differential privacy. So I'm showing here two paintings, Starry Nights by Vincent van Gogh. The one you can, on the left, you can see in Paris. The one on the right, you can see in New York City. And there is a 1 year between these two versions of the same painting. And during this year, Van Gogh developed some mental disease and his perception of the world has changed. So you can think of the Starry Night on the right as a noisy version of the original painting on the left, right? So, but the interesting feature of these two paintings is that they have a very similar value. So they're all priceless, meaning that, and this describes the goal of differential privacy. We want to add noise to data, but we want to preserve its privacy. And that's exactly what we are doing for power systems and data sets. For data sets and power systems, we consider a typical problem like an optimal power flow problem that wants to find the cost optimal dispatch that satisfies power balance and other network constraints like power flow limits. And you can think of different entries to this problem like demand, cost coefficients, or power flow limits as a sensitive data that you would like to release some synthetic version of this data. And we do it for, in this example, for transmission capacities, but we can also go broader and release synthetic version of loads, cost vectors. And the question, how do we do it in differentially private way? So the first step is to take the original data, F bar, and add Laplacian noise that respect epsilon differential privacy parameters. The problem is that the moment you add noise to this information, most likely it will be infeasible. And there is a brilliant work from Georgia Tech by Pascal van Hendrik, Nando Ferret, Terence Mack that show that we can solve a simple projection problem that will try to find the closest counterpart of this of the synthetic data that will be feasible with respect to embedded OPF problem and cost consistent with the OPF problem. And that was a great work that really inspired our research. One challenge with them is that they restore feasibility and cost consistency with respect to a single instance of a load or realization of wind power. So this data set can be very good with respect to peak load or some peak net load. What we like to do, we like to produce high-quality synthetic data sets that will be consistent with respect to population of different instances of OPF problems. Say we have a system operator with operational records, and we would like synthetic data set that will be cost consistent and feasible with respect to entire population of these records. And for that, we use a standard Laplace mechanism and some addition to it exponential mechanism to provide this guarantee. And our mechanism works in the following way. So we take the original data F bar and we add Laplace noise to obfuscate this information in the first step. At the second step, we like to compute the cost difference between OPF cost on the real data and OPF cost on synthetic data. And since we use the real data in this computation, we also need to add some Laplace noise to obfuscate this information to preserve privacy. We then compute the worst case cost on the model that we identify to be showing the biggest difference between synthetic data and real data. And then we solve a post-processing bi-level optimization that computes post-process the data from the first step in a way that it is feasible with respect to worst case OPF model and cost consistent. And then we repeat these steps t times in order to pick more worst case OPF models to improve the quality of the data with respect to population of the records. And because it's a repeated process, we use the real data a lot while we try to obfuscate it. We need to scale parameters of epsilon differential privacy in order to minimize the privacy leakages. But okay, that was some theory, but here is the result. So on the left, you see application to standard Laplace mechanism. What it's doing, it takes the real data. Here you see transmission capacities from IEEE 73 RTS system. They give a real capacity given in blue, and in red, these are the bars that basically it takes a real capacity and add random zero mean random noise to this. And the problem is that with almost 100% probability, this data set will not admit a feasible OPF solution. If we try to restore feasibility of OPF with these capacities, we will be 14.2% away from the optimal solution on the real data. When we look into our algorithm, transmission capacity obfuscation algorithm, after one iteration, we see that our synthetic capacities are much closer to real one, but still obfuscated. But we're still infeasible with respect to 98% of operational records. So, but we can increase iteration counter, and here you see how synthetic data set changes over 10 iterations of the algorithm. The algorithm picks up selected transmission lines and adjusts its capacity in order to restore the feasibility with respect to 1,000 OPF records, and also bring it to the same cost value as the original information, while still preserving privacy. And that's how a synthetic privacy-preserving synthetic data set of transmission capacity data can be executed. And very similarly, we release information about electrical loads. We also extend this, this is a different perspective to the same problem. So that's how algorithm works. So we can specify alpha. It's basically a privacy parameter. You like your original capacity vector to be distinguishable from any other capacity vector within the distance plus minus 5 megawatts. It's a small privacy requirement. You can increase it up to 30 megawatts with our algorithm. But the more your privacy requirement increases, the more noise you need to introduce to original data. And hence more infeasible it becomes at the early iterations, and more suboptimal it becomes with respect to the real data. But over iterations, you can restore both feasibility and cost consistency of your synthetic data. We also did similar releases for machine learning data sets. One instance of machine learning data is a wind power generation. So you can have a data set of n records with power measurement being some function of a meteorological data like wind speed or wind direction, but also rotary angle on your wind turbine. And we have an algorithm that includes similar steps. So we take the real measurements and we add Laplacian noise to obfuscate these measurements. We then estimate regression parameters on the original data and add some noise to them to obfuscate this original data. But we know how regression outcomes approximately look like on the real data. And then we use synthetic data set post-processing in order to process the synthetic measurements to match the performance, regression performance of the original data. And this is how it looks like. On top, bar, you see application of standard Laplace mechanism, only step number 1 in the algorithm. And here you see synthetic data set and you have a real data set. This is a regression line, and we like that our synthetic data set behaves very similar to the original information with respect to parameters of this regression model. On the bottom plot, you see the performance of our algorithm. And on top, we specify privacy requirement. As alpha will grow, the more privacy requirement we will have, the more noise we'll introduce. And we'll see you how outcomes change when we increase alpha. You see that with standard Laplace mechanism, regression agnostic, it just adds noise to data, and synthetic data completely loses any touch with the original information. With our algorithm on the bottom, we add noise to the original data, but then we post-process it so it behaves very similarly to original data with respect to the regression parameters of the regression model. And that's how we can release wind power records in a privacy-preserving way, but also that the data preserve its value, right? So we believe that there is a big future for synthetic data set generation power systems. And if we used to say about synthetic data sets that they bear no relation to actual grid, that it's fictitious data or it doesn't model the operations of the actual grid, using a differential privacy algorithm, we can say a different thesis. We can say that the synthetic data set is produced based on the data from the real world power system. We can give formal privacy guarantees that it's not possible to infer the real data from the synthetic data set. And we can also give performance guarantees saying that computational results on the synthetic data set are consistent with the results on the real data. It means a lot for electricity market operators because we provide the means for controllable market transparency. We can release information about the underlying infrastructure that participates in the market clearing problem. We can also release the data that was impossible to release before, such as sealed bidding quantities or price bids. Now we can release some information about these bids in a controllable manner. There is no need of aggregation anymore. We can release high granular data in a privacy preserving way. So we can release some information about the system while preserve the privacy of the original data. We also provide a rigorous privacy quantification, and it also helps to hedge your any legal consequences as a result of data release. So no one wants to go down to prison for releasing infrastructure data from one of the ISOs. But if you have a rigorous mechanism that can formally guarantee privacy, so you can also safeguard your legal, you can ensure legal compliance. And this technology is already used in many industries, and we believe that energy is the next industry to adopt this technology. I asked at the beginning the fundamental question, where data should go. Should it be private? Should it be public? And with our epsilon differential privacy algorithm, we can provide a non-discriminatory answer to this question. And epsilon is our control parameter, where we can control how much data remains in the private hand and how much is revealed to the public. Thank you all for your attention, and I'll be happy to take your questions.
Thank you so much. And are there any questions in the room?
Hi, Vlad. Interesting talk. This is Ramirez from University of Vermont. So this might be a very naive question, but one thing I was thinking about while you were giving the talk is, did you ever get a chance to, say, run a machine learning model on the real data, and then you created the synthetic data from the real data while preserving privacy? And did you see what the sensitivity of the model was? Now, it might be that the model has very high variance, and so it's bad on model's part. But if the model was good, it would also give some insights on how good this synthetic data generally is.
Yeah, that's a very fair question. We estimate machine learning parameters on the real data, and we use it as a benchmark to restore the usefulness of the synthetic data after we add noise. And the amount of noise that we need to add and estimate the parameters of machine learning on the synthetic data is exactly proportional to sensitivity of the model to input data sets, right? And that's exactly what we factor in when we decide on the magnitude of noise and the post-processing optimization that we use in our algorithm. They're exactly proportional to sensitivity of the model to data. And you don't been lucky when the model is not so sensitive. So it's actually just a small amount of noise to be added in order to privately estimate regression parameters, right? But there are indeed cases when you need to add a lot of noise to obfuscate the data. But that's where you are less lucky. There are also instances where machine learning model might not be sensitive to the private data, but it might be sensitive to public data. For example, in the case of wind power curve that we fit, we saw that the regression outcomes are very sensitive to weather information. But you don't need to add noise in order to obfuscate weather information. It's a publicly available information, everyone can look it up, right? But it ended up to be very insensitive to the private measurements. And we could leverage this fact in order to control the magnitude of noise that we add so as to preserve the value of the data. I don't know if it answers your question.
Great. Any other questions in the room?
Yeah, thank you for the next presentation. I have two questions. So the first question is like you present two examples. One is related to the transmission line capacity constraints, and the other is related to wind generation. So they are both kind of continuous. So how about like the location of generators or location of the lines? They are kind of discrete. How to preserve this kind of private information? That's the first question. And second question is because we need to do this kind of preserve information separately, like for transmission line capacity constraints or for the wind generation. So when we aggregate all this noise together, so all these errors will be kind of propagated, aggregated. It's really hard to recover a feasible solution to the original problem.
Excellent question. So just let me answer to the last question first. Yes, indeed, the more information you need to protect, then the more noise you need to introduce, and it's more challenging it gets to restore feasibility. Not just, of course, it's very difficult to do it with respect to entire population of OPF records, but even for a single instance, it gets very difficult. So, but here, so you need to be very careful when you choose categorize information as private and it's not private. Again, noise proportional to sensitivity of model outcomes to input data sets. Some information is very cheap to protect because of small sensitivities. Others is very expensive in terms of the noise, hence more feasibility. But the power of our algorithm is that it's iterative. It has several chances to restore the data, to restore feasibility of the synthetic data set. And because of this inherent iterations, so it gets very helpful to resolve this challenge when a lot of information we need to protect. So I hope it answers your second question. Regarding your first question, indeed, we protect here continuous data. And I think our algorithm is exceptionally good for continuous data. There are a bit more challenges when it comes to protecting the discrete data. You'll be surprised, but when all the synthetic dataset generation trend started in machine learning, the first data that we were protecting was discrete data, but it was given in the sense of histograms. So the moment you can represent your unit commitment information or some other discrete data in power systems in the form of histogram, there are good algorithms that can help you solving this problem, synthetic generation of a histogram data, right? But it's location, position, right? Location of a generator can be discrete if a generator is present in this node or if it's not, but it can also be continuous, like coordinate on the map, right? So we were thinking how we can enable privacy of locational data, but then what we realize is that there is information that sometimes it makes no sense to protect, because a powerful adversary can just leverage Google Maps to understand where the power plant is located. So you can sacrifice a lot of optimality of your synthetic data and release information in a privacy preserving way, but there will be some backdoor that the adversary can use to infer this information, right? So it's indeed very challenging to protect, but sometimes it might not make too much sense to do it unless you have some other application that I just don't think about at the moment. Yeah, but I hope it answers your question.
Okay, thank you so much. And then we do have one online question.
Yes, hi, we have a question from Dick O'Neill. Dick, I'm gonna enable you to unmute yourself.
Yeah, very interesting presentation. So my one question is, how do you mask the topology of the network?
Yeah.
I mean, I think that characterized as one of your discrete variables, whether or not the line is there or not there.
Yeah, that's no, we don't protect this information. So we take it as a public knowledge. So we're thinking of a big specially distributed grid, a high voltage grid. And yeah, that was the case that I was trying to make. It's very likely that this information can be inferred anyways. So we just don't protect this information. If we do, there are a lot of work to be done to obfuscate this information. Yeah, I just don't want to speculate. So we consider that a topology is given for this algorithm and it's public knowledge, but this is a continuous data that is subject to obfuscation. But yeah, it's a good challenge to address, in fact. So yeah, that will be my comment.
Thanks.
Okay, thank you so much. And if there are no other questions, thank you again to Vladimir. And I believe we're going to take a quick break before the next session. So enjoy. We'll be back at 3.
So can I plug this in or are you still charging? My iPad into your connector. Okay.
Membership sharing?
Yeah, they said that they're gonna check photo IDs at the, the self-checkout. Problem is that people are using other people's cards, and sharing them with relatives. And that's not allowed.
Nikki,
Yes,
you unplugged it.
I asked you and you said yes.
You plugged it in the last time. Don't you remember what you did the last time?
I didn't look. I just asked if I could do that.
Do what you, I thought you were asking if to do what you did the last.
Monica, can you accept the promotion, please?
All right, our first presentation is going to be from Dr. Jesse Holzer. The simulation of All right, simulation of wholesale electricity markets with capacity expansion and production cost models to understand feedback between short-term market procedures and long-term investment incentives.
How does this one work? That sounds okay to me.
We need the slide deck numbered 50.
Bear with us for just 1 second, guys.
Thank you. I'll know soon enough. Thanks. Yes, my name is Jesse Holzer. I'm from the Pacific Northwest National Lab. I'm presenting some work that I've done with Abhishek Somani, Brent Eldridge, and Diane Baldwin, all of us from PNNL. My presentation that you'll see in the slide here is titled How Load Flexibility Can Set Wholesale Electricity Prices in a Wind and Solar Future, Production Cost and Capacity Expansion Modeling. And you'll see that that is somewhat different from the title that appears in the program. And really this reflects a, I guess, last minute change of emphasis and more in terms of the work that was ready to be presented today. All of this work that I'm talking about is a result of some really stimulating, fascinating conversations that I've been having with my colleagues, Abhishek, Brent, and Diane. This is sort of my thoughts on where we go from there. Next slide, please. Thank you. So what we were talking about is this question. So how will marginal cost pricing of wholesale electricity work in a future where much of the supply has zero marginal cost? So sorry, these are not the right slides.
Do we have a more recent set of slides?
Give me a second, let me check.
Is Rodney ready to present, possibly?
Yeah, I'm ready to go if that works.
Why don't we skip to Rodney and then we'll come back to Jesse? Does that work for everyone?
Works for me. Should I go ahead and share my screen?
Yeah, go ahead.
Gotcha. All right. Is this audio good, by the way? I was going to get my headphones in, but those are not in the greatest of shapes right now. So I hope this works well enough.
We hear you loud and clear.
Perfect. Okay. So let me go ahead and share this first. And let's see. All right, can you all see the screen?
Yes.
Okay, looks like it cycles through for me. There's a bit of a delay and a lag. Usually I have my screen sharing going in my video, but we'll go ahead and make that work. So we'll go ahead and get started. Name is Rodney Casito, and I'll be sharing some work that was worked on by Dr. Gary Doris and David Miller concerning how making the right resource choice requires making the right model choice. So here's our agenda for the day. I'll do a quick intro about the authors of the paper that this presentation is based on, and then we'll get into the concept of model limited choice that they discuss and how it breaks down. We're talking about energy production modeling and resource planning. I'll cover some of the changes that we've seen in grid dynamics and energy markets as a result of the increasing renewable penetration on the grid, and close out with some slides on production cost modeling and how choosing the right model is very critical, especially in this renewable rich future that we're moving into. All right, so let's quickly start out by mentioning the authors of the paper I'm presenting today. So Dr. Gary Doris, he's the founder, president, and CEO of Ascent Analytics. He has more than 30 years of experience with energy production modeling from both the physical and the financial risk aspects. Dr. Dorsey's leadership and expertise have really helped Ascend Analytics grow to develop a variety of software solutions that have been used by more than 150 different energy companies here in the US as well as abroad. And he also served as the lead expert witness for Merrill Lynch during the Enron proceedings. Then we also have David Miller, who's a former Ascend employee and currently works for, please forgive me, I did not look up how to properly pronounce the company's name, but we'll go with Wholesale Energy. Now, David has more than 20 years of experience in the power sector, with most of his background being in energy economics analysis and energy policy. And then, of course, I'll be your presenter today. Again, my name is Rudkevich, and I'm the Senior Manager of Analytics and Services at Ascend Analytics. I recently joined Ascend after 2 years of working with the Solar Technologies Office at the U.S. Department of Energy. And my education and research background are in power system optimization and predictive analytics with machine learning. And then the paper that this presentation is based on, this paper was published in 2021 by the National Regulatory Research Institute. And the paper basically highlights the benefits of new age or new era energy resource planning models and discusses how today's legacy models really fail at capturing some of the changing physical and market dynamics of the power grid as we see more and more renewable energy coming online. All right, so what exactly is model limited choice? So model limited choice is a bounded rationality that can happen really in any situation where models are used as the main approach for identifying potential options. So the options or choices are limited by how well the situation can be modeled, the structure of the models being used, and how well those model results can actually be applied to the decision process. So as renewable penetration continues to increase, the power grid is becoming more and more complex and variable, which means that the models that are used for energy system planning should be capturing the changes that we're seeing in the physical and market dynamics of the grid. And a failure to capture these changing dynamics is what leads to model limited choice, which in the case of energy system planning can lead to things like inaccurate valuation of energy resources and increased risk to the power supply business and its customers in general. Now, one of the best ways to avoid model limited choice is to make sure we're not using traditional or legacy planning tools of the past when we're modeling the new renewable heavy grid of the current day and of the future. So in production planning, model limited choice can be experienced in different ways, most of which we do typically see in legacy planning tools. So I'll summarize those first three and then go into a little bit more detail on the rest in the following slides. So first we have unmodeled volatility. Now things like weather, load, power market fluctuations, and wind and solar production. These things tend to vary across time from day to hour, and even from 1 minute to the next. And capturing this type of volatility requires really complex modeling the legacy planning tools generally don't have. And then legacy planning tools also tend to experience what's known as a time step bias. And since renewable production varies so much on a minute-to-minute basis, flexible energy resources can be used to help maintain that overall balance of supply and demand that a power system needs. So modeling tools that use only hourly time steps are not able to capture the true value of energy supply that comes from flexible resources. And to do that, production planning needs to use sub-hourly modeling, which can capture the value of a flexible energy resource that's able to respond well to some of the volatile real-time prices that we see, with quick startup and ramping times at very little to almost no startup costs at all. Then we also have perfect foresight, which is when an optimization model is able to look ahead in the future and know all the future states of weather, load, renewables, and market prices, and can then use this information to help make optimal decisions for dispatch. Now, the issue with perfect foresight is that it tends to overlook forecast errors in renewable production and load, which then results in underreported startups and shutdowns that actually occur in reality to account for some of the forecast errors in production and load. Now, one of the main differences in energy planning models is whether the model is deterministic or stochastic. So for deterministic models, these are more static and take a set of inputs to produce a single estimate of the output. And they're more basic and lack the ability to really capture the uncertainty that we see in the modern day power grid. And this is where the stochastic models can come into play. Now, stochastic models, which are also sometimes known as probabilistic models, these models can use simulation techniques to produce many different possible outcomes of the planning process while capturing the randomness and correlation between the variables of the model. And as I stated earlier, of course, things like weather, customer load, and renewable generation and power market pricing all experience this uncertainty and volatility. And failing to accurately capture and use the uncertain information in each one of these can lead to negative impacts for a power supplier's production planning, which then make it really difficult to truly properly assess business projections and risk. So energy production cost planning in the present day, a good amount of decision makers in the present day do still use deterministic approaches when they're modeling power system dispatch and financial decisions. And this is partly due to a carryover from computing limitations of the past that really made stochastic modeling impractical, just due to how expensive such complex computing was. But over the last decade and change, we have seen great progress in computing power and capacity to where this high level computing is a lot more affordable now, which then allows for sophisticated modeling like stochastic optimization and machine learning to also be applied to our planning tools. Now, advanced modeling tools that are available today not only capture uncertainty in weather and load and prices, but they're also able to model at a sub-hourly level, which removes those past limitations of hourly modeling that production cost planning had relied on for decades. Now, this also comes at a great time for energy production planners, since, again, we are now in a world where some of this old school modeling approaches are not able to really sufficiently support the renewable heavy grid as we continue to move towards decarbonization. Now, there are still some hurdles that we have to overcome, like making sure that power operators and planners have trust in these new and advanced modeling tools. And securing the trust of those who actually use the planning tools will really go a long way in helping the industry ultimately transition towards more advanced production cost planning as a whole. Now, the increased renewable development that we're seeing on the grid has also affected the dynamics of the grid and power markets. So since renewables behave so irregular and volatile, it also causes volatility in the power markets as well, from a seasonal standpoint to daily, to hourly, and down to minute by minute. And since the grid does need to maintain a balance of load and renewables to remain stable, we actually now have a good market for flexible energy resources like storage batteries to help provide some of that quick and fast balancing of power supply and demand that's sometimes needed on the grid. Now, some of the trends that we've seen in power grid and market dynamics are listed there, and I'll go over each one of those in the coming slides. And these changing dynamics are really another reason why the industry needs to move towards using more advanced production cost planning tools. We ultimately want to use models that capture not only the renewable uncertainty, but also the changes that that uncertainty leads to, especially in energy markets that really have a large amount of renewable penetration within them. So the first trend I'd like to cover relates to power prices. So as renewable production in the grid increases, we're also seeing an increase in how volatile real-time power prices have become. Now, that first chart over there on the left, that chart shows the trend between increased renewable penetration and power price volatility in 3 different ISO markets. Now, that volatility value on the chart is a measure of the cumulative daily 2-hour spread in real-time market prices. And to kind of show how flexible resources like batteries can really help in such markets, that volatility value can be looked at as a revenue upper bound for what would be a 2-hour battery that cycles once per day at 100% efficiency. And then the second chart over on the right, that one shows the volatility in location marginal pricing, or LMP, for real-time and day-ahead markets. Now, within real-time markets, we're seeing increased renewable penetration lead to these large spikes in power price that may last about 5 to 20 minutes in duration. Now, these short-term price spikes happen sub-hourly, which further increases the need for sub-hourly modeling and the need for flexible resources like storage batteries, which can really provide great value in power markets that experience such short-term price spikes in their real-time power prices. And then this slide here covers two other trends that we're seeing on the grid as more renewable production is added. So as the renewable penetration increases, we've seen increases in both curtailment and the frequency of negative prices. Now, as most of you here know, power curtailment is intentionally reducing power output below what it otherwise could have been due to things like transmission constraints on the grid or when there's a need to balance energy supply and demand, especially during peak generation hours. Now, from a business perspective, curtailment means a loss of potentially useful energy, which can, of course, negatively impact PPAs or power purchase agreements. Now, those two charts over there on the left show how annual curtailments have increased since 2018 in SPP and CAISO. And this is a trend that we expect to continue seeing as more renewable production is added in the coming years. And then for negative prices, these occur when, of course, there's a surplus of electricity in the power market, and which can happen when renewables produce a large amount of electricity that exceeds the grid's demand, but is not able to be stored for later use. And in such situations, the power producer may offer negative prices as a way to incentivize maybe wholesale power consumers to take on that surplus electricity rather than reducing their output, and to also keep the grid from being overloaded. And that chart there on the right compares how frequent negative prices were witnessed in 2013 versus 2019. And similar to what we saw with curtailment, the increase in negative price frequency can also be attributed to that increase in renewable penetration, all of which just further speaks to why it's so important that production cost models are able to capture these trends that we're witnessing. Now, for all my sports fans out there, this slide here paints the picture of how volatility impacts energy resource selection using an Olympic sports example. So legacy models can use sampling or averages of what a typical day or week looks like when they're optimizing resource selection for energy production. And again, this was a sufficient way of modeling prior to the renewable energy boom. But now, the present day grid really requires more advanced modeling that can help power suppliers find the best plan across hundreds of possible future conditions of the grid. So on the right side there, we have some very elite level athletes who specialize in swimming, running, and cycling. But then we also have the triathlete who is elite at all three of these sports. Now, the triathlete is the type of model that's needed for energy resource selection in the volatile and uncertain power grid of the present day. We ultimately want models that can select a resource plan that performs well in any future condition of the grid. And to do that, the model needs to be able to analyze various different future possibilities and then select the best one. And a quick personal side note before we continue on, I've always been a huge fan of triathletes. I believe they're a completely different breed of human. It's extremely difficult being the lead at any one sport, let alone multiple different ones. So a shout out to the Sam Longs of the world. Now, these next three slides, I'll give an overview of production cost modeling and then break down the differences between legacy and advanced PCM. And I'll also like to note that the authors of this paper refer to these as traditional PCM for the legacy modeling and high definition or HD PCM for the advanced modeling. So I'll use those same terms going forward here too. Now, in general, PCM simulates power system operation and provides an outlook into the uncertain future conditions of the system, which then allows utilities and power providers to be able to strategize and make the most optimal decisions for power supply and production. Now, the accuracy of the future outlook that PCM provides is what helps determine what energy resources will be the most economically beneficial in providing that reliable power supply for an energy portfolio. Now, the image there shows an example of a PCM that takes in simulations of things like weather, renewables, load, and force outages as inputs, and results in outputs of hourly renewable generation, curtailment, and dispatch of energy assets. And then this slide here summarizes some of the main benefits of using high definition or HD PCMs, from their ability to capture the uncertainty in load and renewable generation, to how they can model at an hourly and at a sub-hourly level, and their ability to account for price volatility and some of the other changing dynamics that power markets and the grid are seeing as more renewables continue to rise. And from what recent history has shown us, the total cost for these renewables should continue decreasing over time, while society's push towards decarbonization continues to increase, which again is why it's so critical for the energy industry to really push towards adopting these more advanced or high definition PCM approaches. Okay, now this is our last slide. And it compares model valuations of traditional and deterministic PCMs to the valuations using high definition and stochastic PCMs. Now the table there shows model valuations of adding each of those energy resources or technologies to an existing energy portfolio. And the objective of each model was to minimize the net present value of the cost that it would take to maintain that same level of reliability in a portfolio over a 20-year horizon, given the addition of any of those resources or technologies to that existing portfolio. Now, the results show how model limited choice affects resource selection in the planning process. And looking at the ranking columns, we see that the rank order is almost completely reversed when using the HD PCMs compared to when using the traditional PCMs. We see how combined cycle and gas turbine are the top choices when using traditional PCMs, which makes sense since those two technologies use conventional generation, and for really the past several decades, those have been the go-to options when adding energy resources to a portfolio. But I'd like to point out how the standalone battery goes from being the least valuable under the deterministic PCMs to being the most valuable under the HD or high definition PCM evaluation. Now, this significant change in rank further shows that legacy models do a reasonable job of valuing conventional energy resources like gas turbines, but they're not able to truly capture the value of new technologies that are needed for renewable integration like storage batteries. And this is because the legacy or traditional models tend to understate the economic value of flexible generation resources like battery storage. And to truly capture the economic value of storage, we need to use the HD PCMs, which can model sub-hourly at that 5 to 15 minute level, where flexible resources can really provide great benefit in handling some of those short-term spikes in power market prices that we discussed in the previous slides. And a similar flip in ranking is also seen for the battery plus solar option when you compare the traditional and the HD PCM valuation for it. So since the traditional PCMs are not able to capture the uncertainties in weather and renewable generation, they end up undervaluing what solar can provide as an additional energy resource. But we see that the battery plus solar resource is the second best option under the HD PCM valuation, only behind the standalone battery. And that's mainly due to the increased capital cost, of course, that it would take to add solar to make that a hybrid system. Now, even though the difference in NPV cost doesn't appear to be too large between the two modeling approaches here, decision makers at utilities and other power suppliers do consider these type of rankings when they're deciding on the best option in resource planning. And a lack of understanding and trust in some of these newer modeling approaches can lead to a continued dependence on legacy or traditional planning models. So the trust aspect is still a hurdle that we have to overcome, as I said earlier. But at the end of the day, relying on legacy modeling will lead to making legacy decisions, which is really not sustainable as renewable penetration continues to increase in the present day and in the future as our power grid continues to move towards decarbonization. And that concludes my presentation. Thank you all for listening.
Check, can anyone online hear us?
I'm able to hear you here. Are you still able to hear me?
Yes, were you able to hear the question that was just asked, or did we cut out?
Yeah, I wasn't able to hear that.
Dr. Holzer, could you repeat that, please?
Yes. So I was asking about what's new in Ascend Analytics and HDPCM. What would be a new feature that you could tell us about that we haven't seen?
Gotcha. So one of the new products that we have coming out to include to our suite is our market intelligence, or Ascend MI as we call it. And this helps. So Ascend MI accounts for some of the market impacts of increasing renewables and storage deployment, while incorporating the effects of regulatory and policy landscape changes as well. And it's also able to calibrate hourly and sub-hourly price volatility to help ensure that it reflects some of the observed price dynamics that the market is showing now as more and more renewables come online. It's able to seamlessly integrate into our more legacy and our larger platforms that have been used by a lot of our clients, which are PowerSim and BatterySim. So the market intelligence fundamentals that come from that can seamlessly be pulled into PowerSim and BatterySim for usage as well. And it basically leverages up-to-date forward market data to help provide some long-run fundamentals that can help provide better risk projections for whoever the client is trying to utilize that for. So that's one of the big ones that we have since I joined recently. Let me see, there's another one. We're also, there's some expansions that we're adding to our PowerSim platform to be able to better handle some of the imperfect foresight aspects that go into the modeling. And there's, of course, new UI releases that have come out that make being able to view and utilize all of these things a lot simpler in the new version of PowerSim, which is PowerSim 5 that's now available versus old previous ones, if you're familiar with any of the old ones. Though I joined since PowerSim 5 came in, so I'm not too in tune with what PowerSim 4 and the other ones were like, but I do know those are some of the key changes that we have added recently.
All right, Dr. Quezito, thank you. Do we have any other questions in the room? Anyone online? All right, thank you very much.
All right, thank you all.
All right, Dr. Holzer will give this another shot. Can we get the slides labeled 50 brought up, but they should have been uploaded more recently, and there's a tagline that they're corrected. So this should be 16 pages for these slides?
Yes. Okay.
You page forward a few slides just to make sure we have the correct ones this time. Going until you hit an image of a car charge. Are these good? All right, back to the start. Thank you very much.
Okay, thank you, Dr. Quezito and the conference organizers for helping me with this slide issue. My presentation is how load flexibility can set wholesale electricity prices in a wind and solar future. This is work with my colleagues at PNNL, Abhishek Samani, Brent Eldridge, and Diane Baldwin, who to thank now for the many stimulating conversations that we've had that resulted in this presentation. Next slide, please. So our motivating question is, how will marginal cost pricing of wholesale electricity work in a future where much of the supply mix has zero marginal cost? So we think of the current market procedure as something like a merit order dispatch, where the marginal cost of the last dispatched resource sets price. So if you look on the plots here on the right, I've got a supply and demand curve with conventional resources. So the supply curve shows a steadily increasing price. And then the demand curve is really just a vertical line. And where the line intersects the supply curve, that's the market outcome. In a future of wind and solar, we anticipate that much of the supply will have zero marginal cost. And so we have a concern that the market prices will often be either near zero, negative, or just too often equal to zero. And so how will generators earn enough money to remain in the market? This motivates questions about what we should do about this. So do we need a new dispatch method that's not really based on the marginal cost? Do we need to somehow price uncertainty? And in general, I'm very interested in exploring new dispatch methods and methods of pricing uncertainty. However, for this talk today, I want to focus on how something like the old method, marginal cost pricing, can maybe just in some cases, but can continue to work. And what I'm going to focus on there, so next slide, please. And what I'll focus on in this hypothetical answer is that what can cause the old method, so-called marginal cost pricing, to continue to work well in a future like this is load flexibility. So specifically that loads that can turn down or turn up their consumption for a given price can often wind up setting the marginal price in a wholesale market environment. Some points that I'll want to explore in this hypothetical answer are that the incentive to develop, deploy, and operate load flexibility technology is just the same, really, as incentives to develop, deploy, and operate other energy technologies, and they're essentially derived from the market prices. So a thing that I'll want to explore is that this incentive to deploy load flexibility technology will get stronger as wind and solar gain market share. And then we might ask why we don't currently see load flexibility or flexible load setting the market price now. So why do we so often see zero marginal prices from wind and solar? And so the conjecture here is that the reason we don't see load flexibility playing that role is that the investment incentive is not strong enough yet. In other words, it will be. Next slide, please. So just a quick note on what I mean by load flexibility. So I'm talking about loads that can provide flexibility, and this is coming from a sort of vision of the future where practically everything that we do runs on electricity. And I'm also thinking about loads like data processing, electric vehicle charging, and residual loads where residential loads that are controlled by smart devices. The common feature of this idea of load flexibility is that the load needs to participate in the market clearing procedure. So that could mean different things. It could mean that the load is not a fixed quantity, but it is an elastic demand bid. So it's actually bidding a price and a quantity, just the same way that generators now bid prices and quantities. And that kind of load flexibility is present in markets today, not necessarily to a great degree. But in addition to that, it could just be, again, a fixed quantity of demand, but with some known price elasticity such that if the price changes, then the demand would change. And that price elasticity need not be a bid that is submitted by the load. It might be something that would be estimated statistically. So that might be estimated by the market market manager. Next slide, please. So to explore these questions, I'm working on some models. So first of all, there's a very simple, really coarse capacity expansion model. So this is a linear programming model with continuous variables for the capacity installed for each technology. Another model that I've got going for this is a more detailed capacity expansion model, and this is just a mixed integer programming problem where you have integer numbers of generators built for each technology. And lastly, I'm working on a production cost modeling simulation where we would actually model the individual generating units and run the simulation in a sort of rolling horizon fashion. Next slide, please. So for the coarse capacity expansion model, the way that this is working is so it's got a few different electricity technologies, conventional generation, renewable generation, and some load flexibility technologies, load increasing and load decreasing. And what the model decides is how much of each of these technologies to install. Then given that amount of technology installed, it clears a sort of a model market for the supply and demand of electricity. So it's actually clearing the load decreasing and load increasing technologies at the same time as clearing the generation technologies. Okay, so next slide, please. So here are some details on this. This is so the objective is to maximize really a market surplus minus the cost of investment. Each of the technologies that I'm interested has an installation cost or an investment cost, and each technology also has operating costs. So that would be something like a cost per megawatt hour. So it's going to maximize the total of, well, let's see, all of the positive terms there are values, and all of the negative terms are costs. So the one positive term, the value term, is the value of load. And then all of the negative terms are the cost of serving that load. And then there's an energy balance constraint where we add up all of the demands, and that should be equal to all of the supply. And there's a multiplier that gives you the price. Somewhat critical to the model is that there are bounds on the installed capacity. So you can't just install as much load decreasing technology as you'd like. There's some idea that we've got a resource limit. And then so wind and solar are represented by renewable generation as a single technology here. And so each of those has a variable representing the amount of energy supplied by that technology in each time interval. For variable generation, the upper bound on the energy that it can supply depends on time, so that I'm modeling the variability of renewable generation there. And then one final interesting constraint is that the capacity installed of load decreasing technology can be no more than the total load. So you can't install load decreasing technology that drops the load below zero, essentially. Next slide, please. So to get this model up and running, I've got a year of representative hours, but they're just the load and the renewable generation are just distributed randomly. So it's not like they're actual hours in a distribution of load and wind. Then for the investment and operation cost parameters for each of the technologies, I've set it up so that you get a short-term supply and demand curve. And one way that you can think about it is that you might have started with a fixed demand curve, and that's this vertical line at 1,000 megawatts. And by adding a certain amount of load decreasing technology, you get this indentation in the demand curve. And then by adding a certain amount of load increasing technology, you get this expansion of the demand curve here. And then the supply curve is formed mostly by variable generation with zero price, but also some renewable generation with zero price, but also some conventional generation with non-zero price. Next slide, please. So when I run this model, I've run this on 4 scenarios. So first, an economic scenario where the model is free to choose the capacity that it installs of all 4 of these technologies within fairly loose limits. So these limits are all loose enough that basically it'll choose whatever it wants. Then I've got 3 more scenarios. So one where there's going to be essentially all conventional generation, and that has a very tight limit on installation of renewable generation. One with all renewable generation, and that's a very tight limit on conventional. And one where the load flexibility technologies are tightly limited, and you've got lots of renewable generation. And the point to see here is that without load flexibility, the high renewables scenario, so that's this last one, has mostly zero price and otherwise some very frequent price spikes. So that's the red plot here. So what it's showing is that 90% of the time we have price is zero, but then almost all of the remaining 10% of the time the price spikes up to the cap of 1,000. But then with the all renewable generation, but plenty of flexible load scenario, and that's the green one, we got a smoother distribution of prices with at least some significant probability of prices well below the cap. Next slide, please. Then there's another experiment that I want to talk about where I'm varying the limit on the capacity of each technology with renewables going from essentially 0, 10 megawatts to 1,500 and conventional going from 1,500 to 10, so that in these plots, that's going from left to right. So all the way on the left, you've got renewables are limited almost to 0 and conventional is unlimited. And then as you go to the right, you're getting more renewables. And the observation then is to see what amount of load flexibility is deployed. And the point here is that as the renewable capacity share increases, the load flexibility deployed also increases. And what that is indicating is that, at least in the model, if the load flexibility technology exists, then the incentive to deploy it comes out of wholesale market outcomes. Right? So this capacity expansion model is giving us wholesale market outcomes, and that's telling us that the deployment of load flexibility follows the what's happening to wind and solar. Next slide, please.
Time check, you have about 5 minutes.
Thank you. One more thing to point out in the very simple model. So again, we're considering an increasing share in renewables from left to right. And this is looking at what's happening to the prices. So the concern is that as renewables increase market share, you'll get a lot of zero prices. That's a bit imprecise. So the concern really is that the prices will be either zero or a price spike or some continuous version of that. And so what this is illustrating is that the presence of load flexibility makes it possible to get less of a bimodal distribution of prices. So in the top plot, load flexibility is limited to 10 megawatts capacity. And in the bottom plot, it's essentially unlimited at 1,000. And what we're observing is that in the top plot, actually the average price increases while the sort of the 25th percentile and 75th and 50th, so the distribution of prices all generally trends downward. While with load flexibility allowed, the average actually decreases. And so what I think this is saying is that really we're seeing less frequent price spikes. That it was the price spikes in the limited load flexibility case that really caused the average to increase so much. Next slide, please. Okay, so I've also got a more detailed capacity expansion model where I'm trying to include the effects of things like ramping, reserves, and sort of the sequential nature of actual electricity markets. This model comes largely from a paper by Brian Palmentier and Mort Webster. Next slide, please. And I've got data for this model from ERCOT 2022, the load, wind, and solar. And I took some other data from data on conventional generation from a paper by Todd Levin and Auden Boderud. Next slide, please. So basically the point here is that the story is similar to the conclusions in the much less detailed capacity expansion model. So I would focus on the energy prices down here in this table. And maybe the best comparison in a short amount of time is to look at two scenarios. So the high load flexibility and high wind and solar compared to low load flexibility and high wind and solar. And in the low load flexibility case, the median energy price is much lower than in the high load flexibility case. $9 per megawatt hour versus $31 per megawatt hour. Next slide, please. Okay, so I will wrap it up quickly by noting that I am very interested in pursuing a simulation approach to questions like this. So I am building, I've not finished building, but am building a production cost modeling simulation that will explore the feedback between the operational outcomes of price, dispatch, and commitment and revenue and the investment decisions of installed capacities, and with sort of the goal being to consider scenarios where the market rules have a great influence on that feedback. I will stop there.
Right. Dr. Holzer, thank you very much. Do we have any questions from the audience?
Thank you for your presentation. This is Mojda Hetman from Arizona State University. I have a few fundamental questions. So the motivation started from the discussion of zero marginal cost units of renewable resources, correct? So when you have, if you don't have the price flexibility, then if you don't have the load flexibility as your demand and supply curve was showing, at some point in time, you would have non-zero price associated to that, correct? Which is not necessarily a bad thing, can be argued about that. But my main question, well, I have multiple questions. One of them is that when load flexibility, a lot of time is through shifting load, right? So then there would be a shift to some other time, which then that also there needs an analysis of how would that impact the price to begin with, right? So I wanted to hear your opinion about that, for whether you consider anything like that or how something like that can be considered, because overall the consumption need anyways probably is relatively unchanged.
Thank you for the question. So for and I guess I would see two parts in the question. For the point about load flexibility really being, we're going to shift some load from now maybe until later. I think that is really where you do need something like a production cost modeling simulation. So it would be important to capture the idea that in the present moment, I shift some load and specifically a market shifts some load for me. And then there's another occurrence of that market coming up in a future time when the load that I didn't that I put off to another time, now that appears in the present again. And because it was put off, maybe it's even more critical to serve that load now. So I think that to really answer questions about that level of detail, one does need the simulation that I have in mind. For your first point about how at some point you will encounter high prices or you will encounter zero prices. I think so in these conversations that we were having, there was this idea that that you need a certain set of generators on the system just in order to make the system function properly. But then they can't make money because the price is too often zero. But then what happens? Well, some of them leave the market. And then the price is not so often zero. So there's an equilibrium between the investment decisions and I guess I should say disinvestment decisions and the market outcomes. Is that getting to what you were asking?
Yeah, in the same direction, but that's exactly my point too. So that non-zero price is not necessarily a bad thing, because there is also another component that I think is not considered, but I might be wrong, and that's the reliability component, right? So that's also,
I agree that that really is not considered at this point.
Yeah, eventually even zero marginal cost units, there should be a compensation for reliability between. Thank you.
Thank you.
All right, reminding anyone online to please use the Q&A feature to submit any questions. Monica, do we have any questions from online?
This is from Alva Svoboda. And let me go ahead and give her permission to unmute so she can ask the question.
Oh, thank you. My pronoun is he, but thank you.
My bad.
No, not at all. Not at all. I was just curious, and this area that I've been thinking about is in the future that you're envisioning. Are you simply lumping in batteries into the portfolio of demand-sensitive resources? Because I think they have different characteristics from customer load, which to me isn't going to do much more than what you've indicated in your slides. It's going to be useful at times, but it's not going to be something that sets prices in the market on any prevailing basis. So I was curious what you think about batteries in this paradigm.
I both am and I'm not lumping it in. So this is a conceptual model, and as a concept, it's treating any kind of load flexibility all the same. And I mean, conceptually, it's saying that batteries would be a type of load flexibility. However, it also recognizes that, or I recognize that at a certain level of detail, it's very important to treat batteries with their more fundamental properties. And for that, I mean, again, I would turn to something more like the production cost modeling simulation.
Thank you.
All right, I think we have time for one more question from the room.
Thanks, Jesse. This is very interesting. Nikita Singh, Alpha MEPRI. I didn't catch how you determine the elasticity of the load. There was one slide where you did show a decrement in load and an increment in load, but the curve had an elasticity to it. How did you come about getting the elasticity?
Did you ask how did I come up with the elasticity?
The price elasticity, yeah.
It's made up entirely. I mean, this certainly is something that can be statistically estimated for individual loads on a any aggregation you want. But I did not do anything like that.
Thanks.
All right, thank you very much, Dr. Holzer.
Thank you.
All right, our next presenter is Dr. Renan Giovanni. Do you have a second presenter as well? Or would this may be an outdated node?
That's correct. I do have my colleague Joe will be joining me, and actually he will be kicking off the presentation.
All right, and Joseph Franz. All right, you are virtual, so you should have control to start sharing your slides.
And I should be sharing. Do you see the slide?
We see and hear you, and we see the slides. We should be good to start.
Everything worked. Always good when the technology works. Well, are we the last for today?
We have one more presenter after this, so their co-presenter dropped out, and they're going to have to run over here from the other room, so they're going last.
Okay. All right. Well, thanks for those that hung around. Just been some great presentations throughout the day. Lots of very interesting modeling ideas and ways to improve the market. So really appreciate FERC putting this on and inviting GE to present. So let me get right into it to kick this off, and then I'm going to turn it over to Renan to really present the meat of our presentation. So here at GE, obviously we see the grid at an inflection point. The grid can become a bottleneck for energy transition. All things that we've been talking about, decarbonization, energy security, that impact the world in a really positive way, cannot happen without the grid. We believe that for a long time, the grid was a crucial enabler and national essential component of the energy transition. And if done right, software can be an accelerant. As we all know, that hardware takes a long time to deploy. Building transmission lines is incredibly expensive and a long-term challenge. But once that hardware is deployed, deploying software on it can happen much quicker. One of the challenges that we hear a lot from our clients is, what are the regulations at both the federal and the state level, right? Particularly, with some of the new regulations that are coming out in the DERs, which we are hearing about a lot at this conference, right? There's an inherent conflict between those distributed energy resources connected at distribution grids, participating in wholesale markets, right? That needs to get clarified so that the utilities and the ISOs can start executing on that. So here's just a quick look at the complexity, right? We've had lots of presenters today talk about this, the increasing penetration of solar. I particularly liked Hani's presentation yesterday from California, which is to me like a canary in the coal mine, because they're so far ahead of the rest of the nation in terms of seeing the impacts of renewables. Something I saw recently is that, they had the Duck Canyon a Duck Curve a few years ago, and now that's turned into the Duck Canyon because there's so much renewable energy generation coming on in those afternoons, right? And that rate of change is spreading not just across the US, but around the world as well. And this brings an unprecedented complexity to that grid that we've been managing for the last 40 years. It's getting a lot more complex as things are getting connected, a lot more people are connected to it, and there's more omnidirectional power flows going on with that connectivity. We're already seeing the signs of the grid potentially negatively impacting energy transition and slowing things down, in that the interconnection processes at both the ISOs and the distribution companies slowing down. The permitting process of getting new renewables connected is slowing down. Just to spin the wheels back on some of these technologies, I started my career at a distribution company 35 years ago. And my first pilot coming out of college was an EV pilot, because EVs were just around the corner. We'd also toyed with some wind pilots as well, and solar. But now we're seeing all these technologies hitting at the same time at scale, right? And I don't think anybody that's been in the industry long saw all three of these technologies hitting at the same time at the scale they're hitting at, combined with the acceleration of batteries. So it's a very interesting time that we live in with energy, and for the young folks in the industry, this is not how it's been for the last 40 years. So very exciting times to be here. So Renan, you want to take us through some interesting, we've put together 11 use cases that GE's been working on with some of our clients to help accelerate the energy transition. And also Renan's going to talk about some of the current capabilities that are out there that could be helped by regulations, and some of the new requirements that are coming on. Renan?
Yep. Thanks, Joe. Yep. So next slide, please. Yep. So all the 11 use cases that Joe just mentioned are use cases that, in fact, we've been working with our client probably in the last 3 years. Okay, so they are all very, forward thinking, and in every side of the pond, here in Europe or in North America. So we start off with what we call internally as next generation electric markets, right? So we've been our customers in US in order to prepare for FERC 2022, amongst other challenges. They came back to us and asked us if we could, in fact, prepare our market solution to be able to include things as small as we call it here as micro assets, right? EVs, rooftops, for new market services that might happen in the future, such as grid stabilization, black study, and inertia, for instance, that you will see in the next few use cases. So based on that, we start to work with them, in fact, to bring a more modular suite of market solution that could, in fact, deal with more bids and more constraints, and also shorter time intervals, right? So this is one action that we are currently work with our clients. For instance, we have also worked with a few customers on linear state estimation, so complete different domain. Now we move from markets now to the EMS WAMS space. So linear state estimation, for instance, it's fully based on PMUs, and today we have already customers that are receiving 2 million data points per second. Okay, so coming from PMUs, time synchronized, and we worked with a few of those customers to develop linear state estimation, which in fact exceeds NERC IRO 008-2R4 until P001. So with this new technology, we are able now to deliver 60 times per second, a solution every 60 times per second, as opposed to every 30 minutes, which is the current mandate. So it's a completely new solution that can deliver superior speed and robustness over classic state estimation, right? So this is another technology. And as you will see, all those new technologies, because they came sometimes from business as usual, sometimes from innovation projects, they drove us to, in fact, create what you will see in the next slides, which is our grid orchestration software. So going back to linear state estimation. So in one hand, we had markets asking for more bids. Now we have linear state estimation driving us to be able to process more data. Okay, then as a third use case, we have grid inertia. So for instance, here in UK, we have a very an example where we see inertia reducing year after year, and the amount of spent with ancillary services to compensate the lack of inertia also increasing year over year. So one of this also came from an innovation project. We developed a solution where we could then estimate grid inertia based on synchrophasors. But compared to the previous one, where we had PMUs with fast data, lots of PMUs, here we are leveraging PMUs, but for grid inertia, the challenge was not the volume of data, but in fact was the amount of historical data, because we want to also be able to forecast, right? So because you want to know if, how low is going to be your inertia in the next 1 hour ahead, 3 hours ahead, a day ahead, so as you can prepare your grid to survive if you have any challenge, right? So this was a different use case, also, pushing us to create a new set of technologies. Next slide, please, Joe. Just to summarize, new markets come with requirements. Expect an increase in number of bids and offers, expect increase in number of parallel simulation and validation, linear state estimation, volume of data, and grid inertia, long-term historical data. So as you can see, all different domains that our previous generation technology was not prepared to handle.
And
next slide, please.
I was going to say, on the next gen markets too, we've also heard some interesting new products that have been proposed during this this conference that obviously will drive new requirements too.
And now going to our fourth use case. So automated prediction, detection, and planning for outages. So for unplanned outages. So one of the areas that we've been working on, so what we call smart transmission outage and restoration. So traditionally, restoration plans, they are made by the planning department, and then they are executed inside the control room. But today, we have already the technology where this kind of restoration plan and outage could be done and can be calculated in real time. So we were able to demonstrate that we could bring down a typical 7 days to about 3 minutes, dynamic restoration planning, right? And also, by doing that, we were able to reduce the outage by 60%. But once again, we needed, in order to support that, being able to scale and do all those fast calculations in real time, right? Another use case, this is another part of a mandate, a current mandate that is implemented, is FERC 881. So we are now introducing digital DLR. And what is digital DLR? So traditionally, we can calculate the dynamic line rating using the measurements that are coming from the line ends and from the temperature sensors. But with digital DLR, we take this a step forward, and we take, in fact, weather data and combine with weather data coming from every point of your transmission line, so as we can then calculate the ampacity of the line, right? So now we are aggregating geospatial information coming from weather with electrical data, right? And by implementing this approach, we can bring the accuracy of the solution down to 5% accuracy of physical sensors, and having the advantage that you don't need to install the physical sensors, right? So it's a purely digital solution. But once again, it's a new challenge for us because we didn't have a solution that could support at the same time geospatial and electrical, right? So we had siloed solutions that traditionally had their space, but then when we try to create the new use cases as part of the innovation, then we started to stitch things, which was not what we wanted. We needed something that in fact could support all of those use cases. The next use case, for instance, is grid stabilization. We had already Manu today here in one of the presentations talking with more details about grid stabilization, but it was exactly using DERs to stabilizing low inertia grids, so fast frequency response. So was the ability, in fact, to map those assets in real time, understand the amount of assets that are available in different pockets of your grid, understand how to allocate when to respond, right, and respond in the right locations. So as he pointed out during his presentation, and leverage those assets so as we don't need to go after new dedicated ancillary services. We could use existent assets to perform that for us. But the challenge was how to have an architecture, a tech stack that could support that, right? Because with using DERs, we can use for fast balancing. We can, so traditionally people are talking about capacity, but we can take a next step and use that for instance, grid stabilization. We can use for fast frequency response and so forth. And the next slide, please, Joe.
Yeah, I was just going to add on the final point too, and what the other challenge I think when you start looking at these different services the DERs can provide is who are they providing it for? Are they providing those services into the distribution grid and the transmission grid, and are they bidding into both markets? Are we double counting? Right, there's definitely going to be some interesting challenges to sort
discussions.
Yeah,
exactly. Mm-hmm. Yeah, and as we can see, so for instance, for automated prediction, detection, and planning of outage, we have requirements for parallel process, long-term historical data, right? So weather outage, so as we can train the outage prediction machine learning, right? For digital dynamic line rating, we have now the need for grid, weather, and geospatial at a much more granular level, right? And for grid stabilization, low latency, high volume of data. how to do the DR aggregation and control at grid level. So once again, all new requirements that our traditional and classic solutions were not prepared and designed for. Right. Next slide, please, Joe.
Yeah, we're seeing in terms of requirements around the DERs also, some of our clients are looking for forecasts now for up to 5 million points simultaneously on their grid. Massive volume of data.
Time check, you have about 5 minutes.
Yeah, so then to finalize the list of, we have AI-based load DR forecasting, as Joe just mentioned, going to millions of points. Distributed Blackstar was also presented by Manu. So how to perform a bottom-up strategy. And in the end of the day, is not replacing the top-down that we are using, but in fact, having the two at the same time, how you can perform top-down and meet the bottom up. So as you can speed up and leverage the resources that are connected at the DER at the distribution level, right? And once again, but this also depends on a vast amount of data, because especially in the distributed black start, we will see pockets with very low inertia because those will be at the distribution level. So how can you stabilize that grid, fast enough so as you don't drop load when you're restoring? Vegetation management, another use case. Once again, the need for geospatial data and historical data so as we can predict how fast that vegetation could encroach the transmission line path, so as we can create solutions that help our customers to prevently to go and trim those that vegetation, so as you don't have any sort of penalties caused by vegetation problems. And next slide, please, Joe. Summarizing. Grid, weather, geospatial data requirements, low latency, high volume of data, DR aggregation, all the same common topics once again. Next slide, Joe. And finally, advanced storm planning and outage restoration. So the idea here is to actually use long-term historical data to train a machine learning model, where then you can predict where is going to be the most affected part of your grid from a distribution standpoint. And then you could preemptively and proactively allocate your distribution, your crew, your field crew, so as after the storm hits and causes the outage, you have already your crew in place so as you can accelerate the load restoration, right? And finally, T&D integrated solutions, so as Joe has mentioned, we see many parts of the world already a need to an exchange between the distribution utility and the transmission utility and system operator to exchange data from the assets that are connected at distribution level, because those assets are already impacting the transmission grid. Next slide. Once again, grid weather, geospatial data, individual DRs control. And now I hand it back to my colleague, Joe.
Thanks. And I know we're running out of time, so I'm going to just skip this slide and jump to this one here. So underlying all of these new applications, right, for us to work together to, in this new world of energy transition and distributed energy resources that are outside of the traditional grid operations and control framework, right? We need to have a platform, and this is where GE is investing heavily, is in grid orchestration platform for the industry based on zero trust security, so that we can incorporate these DERs that are sort of outside the utility data center and outside their firewalls into being able to dispatch and use them in markets. And most importantly, having a common data fabric between all the different components of the utility grid, right? Underlying all of our market systems and our energy management systems and our ADMS systems, right, is a physical network. And we all have to have a common view of what that network looks like. And so GE is driving to this and welcoming, both our customers to develop applications and partners and startups and everybody to build on this framework and be able to leverage the zero trust security model and the common data fabric. Just a closing point here, since we are at FERC today, again, as I mentioned at the beginning of this we do hear from a lot of our utility and ISO clients that they are, waiting before they make major software investments to move forward to having a flexible operating environment for energy transition. And so we, in addition to sort of the technology speeding up and the software speeding up and the energy transition speeding up, we need the regulatory wheels to speed up as well and clarify rules, particularly around FERC 2222, integration of all these DERs, who's going to control in real time, who's it, I think the first presentation yesterday that FERC clarified, we don't regulate retail energy, we don't regulate local distribution, but at the heart, FERC 2222 is dealing with distributed energy resources connected at distribution voltages, right? So we need to get that all clarified as quick as possible, make the rules clear to the grid operators so they can make the investments to move to the future. And at that, I'll conclude and open it up for questions.
Right. Thank you very much. All right. First, do we have any questions in the room? Right, do we have any questions online? Please use the Q&A form to submit any questions that you have. That was a false alarm. Last call in the room.
I think people have had a long day.
It's been, thank you for bearing with us, and thank you again for your presentation.
Thank you for listening and this opportunity.
Thank you.
All right, finishing the day is Dr. Xiaoming Feng. We'll go ahead and get your slides pulled up. This should be presentation number 53.
Great. You should be able to. Sounds good. Yeah. Okay. Could you bring up the first slides? Okay. Can I start now? Okay. You. Yes. Good afternoon. My name is Xiaoming Feng, and what I'm going to present is the work done by Dr. Sina Gabrielli and me. Dr. Gabrielli, because of personal reasons, cannot attend this meeting either in person or virtually. So I'm going to do the presentation. And Dr. Gabrielli is with Pennsylvania State University, and me is with Hitachi Energy Research. Hitachi Energy is previously was known as the power grid business of ABB. Next slide. We're going to talk about a simple and novel idea of called megawatt-based approach for transmission shortage pricing. Okay, and first, and I will just kind of introduce what is TDC, transmission demand curve. What's the purpose? What's used for, right? And then talk about describe a situation where excessive locational marginal price will result from using a transmission, just a straightforward transmission demand curve in the scheduling model. And then describe some of the existing approaches to address multiple DDC activations. And based on that, we will introduce this megawatt-based transmission demand curve modeling approach and what's the motivation and the idea. And then we'll illustrate with simple examples. And then follow up with the conclusion. Okay, when we do the electricity scheduling, market scheduling, And we have to run a so-called security constraint unit commitment, and then followed by some pricing runs, which is also security constraint dispatch problem. But when we're trying to solve those problems, sometimes there is enough supply in the system, but the system is not, the supplies are not in the right place, and there is transmission constraint. So with hard transmission constraints modeled in the optimization problem, where there is no feasible solution. So we have to relax the transmission limit. Okay, and for each, if you look at this 3-bubble example here, and we have area C, which has a total load of 1,000 megawatts, but a total demand of 2,000 megawatts. And the total import from area A and B limit into area C is only 400 plus 500 megawatts. That's only 900 megawatts plus the local generation in area C. So that's only give you 1,900 megawatts. That's still not enough to supply to meet the demand in area C. So the transmission from A into C or from B to C needs to be relaxed so that we can find a feasible solution. And the way to do it is introduce this transmission demand curve. Transmission demand curve is just an administrative way of applying a penalty for the amount of violations over the specified transmission limit. Okay, and this is a progressive penalty, and when you have a small amount of violations, you have a small amount of penalty, and then it goes up, and it can go from a couple of $100 per megawatt to 4,000 per megawatt in the New York area, New York ISO. So without TDC modeling, if you look at this little table in the middle, and we would have a constraint that says the flow must be less than the limit, right? But with that, there is no feasible solution. So with the TDC modeling, so essentially we take the flow and minus the amount of violation and say that is less than or equal to the limit. And then if the original problem has a feasible solution without relaxation, then the violation will be 0. And then if it doesn't, then the violation will be properly will be determined, which with the balancing between the violation cost versus the redispatch cost. Next slide. Okay, so that solves the feasibility problem, but there is a side effect from doing that. And sometimes that because we can have, because we are solving a security constraint unit commitment or dispatch problem, right? For each of the facility in the system, and we could have multiple constraints showing up in the model. And so if you look at the first major bullet, right? And for each, the A stands for asset, T for time interval, C for different continuous conditions. And then, so for the straightforward application of the TDC concept is to add this violation component to the transmission constraints, which is also indexed to the asset, the time, and the contingents. And then that for each of the violation amount in each of the constraints and all the total penalty cost is accumulated in the objective function and over all the different contingencies. And there is another type of scenario where the multiple contingency activation is across different assets. Okay. So this is represented by this table here. This table across the top, we have the different, in each column, it corresponds to different assets. Each row corresponds to different contingencies. Okay. And so we could have, for a particular contingency scenario, we can have multiple assets that's being, that needs to be relaxed under TDC. So in this expression here, the penalty function here is just simply the cumulative or integral form of the TDC curve, because the TDC curve is just to give us the incremental penalty per megawatt violation. Next slide. So what people have done is to reformulate the security constraint, optimum security constraint unit commitment and the dispatch model. And one of the, to avoid excessive locational marginal price, because when we have this multiple activations and of the transmission demand curve at high levels, and those high levels have extremely high penalty costs, and those costs, when you accumulate them, they make the locational marginal price extremely high, and which both neither the customer nor the system operator like it. So they try to avoid the situation where the locational marginal price is excessively high. One of the approach is used by New York ISO in their research is called the TDC by facility formulation, and they have proposed this approach in 2021. And here you can see the before formulation and the after formulation. Essentially, the idea is quite straightforward. What they did is, instead of applying this violation term to every constraints for the same transmission facility or asset, where the violation has a contingent subscript, and the objective term has an accumulation of the penalty cost over all the contingencies. So after the formulation, then they just use one maximum violation, which satisfy all the contingency relaxations constraints. And then the resulting formulation objective term, you have only one term for the penalty. And this will essentially solved quite nicely the transmission demand constraints curve activation for the same asset across the different contingent scenarios. Next slide. Okay, for the but that does not solve the problem with in the situation where you have multiple TDC activations across different assets. Okay, and in one approach was proposed also by some researchers at the New York ISO. What they have proposed is they try to identify and eliminate what's called the duplicate and the redundant constraints. As kind of shown here, I have a very simple example. The shaded area represent the feasible region without considering the constraints C1 and C2. Okay, but when you consider the constraint C1 and C2, because they are pointing to a different direction, there is no intersection between the feasible region defined by constraint C1 and C2 with the shaded area, so that the problem does not have a solution. And then it means in order to find the solutions, that the constraint C1 and C2 both need to be relaxed, but the amount of relaxation will be different. So what they do is to identify this so-called redundant constraints by choosing the constraints that has the smaller amount of violation. Okay. This idea works quite well if you have constraints that are in kind of parallel or almost parallel to each other. You can compare the right-hand side and to determine beforehand which one will have more relaxations. And in their approach, it requires 2 economic dispatch runs. And there is a kind of an undesirable side effect is what I call the KKT condition mismatch between those 2 economic dispatches. Because in that approach is they identify the redundant constraints. In this example here, the redundant constraints is the blue one, right? Because the constraint, the C2, the red line needs to move further up in order to touch the rest of the feasible area. And the blue constraints represented by the blue line has a smaller amount of violation. So you take away that one, and then you have only one constraint left. But the problem is in the two economic dispatch rounds, in the first dispatch, and after the optimal solution is found, and the solution point is a stationary point that satisfies the KKT condition. That KKT condition has both the multipliers for the constraint number 1 relaxation and the constraint number 2 relaxation. If we remove one of the constraints, if you think of that in a kind of people playing tug of war, right? And the people in an equilibrium on both sides, and now you remove one person from one side, suddenly you destroy that equilibrium, and that the original equilibrium will shift to a new solution, which you essentially here it will move into the interior of this shaded area. So that's I think that has some kind of it's a conceptual and also practical inconvenience. And next slide. And based on that, we started thinking to see if there's any different approaches to solve this problem. And so we started with some very basic ideas and recognition that the current transmission constraints and violation costs in SUC model depends on the megawatt capacity only, right? If you inspect the SUC model, look at one particular constraints, it only says this flow must be less than that, and then the amount of violation you plug in that in the object function with the penalties. And what we believe is the transmission violation cost should be proportional to the cost of transmission capacity expansion, right? You violate it, and how much to fix it in the engineering sense, right? It's not just the capacity, also the distance that matters. So the cost of transmission capacity depends on both the megawatt and also the physical length of the transmission line. And it's independent, should be independent of the arbitrary modeling choices. Giving an example here, if I have a 100-mile lines long between bus I and the bus J, whether I in the SUC model, whether I model it as a two section lines or five line sections, they should give me the same result. They should not produce different locational marginal price. Right? I call that modeling, because those modeling choices are arbitrary, and our model should be invariant to those arbitrary choices. Okay, so the idea of a megawatt-based, mile-based approach is to evaluate the economic impact of a transmission violation based on not only by megawatt, but also by the distance. Next slide. So this idea result a very simple reformulation, right? So essentially, we still we can directly go to the second major bullet. Is this idea is we still apply a kind of relaxation or the violation amount to the constraints, but in the objective term, we scale, we determine, we start with the penalty per mile, which depends on whether it's an AC transmission line or HVDC transmission line, and then multiplied, weighted by its length. Okay, so that if you arbitrarily divide a 100-mile line length line into two sections, then you do not change the overall penalty. Okay, so this will, and this idea will also can be combined with the New York ISO's TDC by facilitator approach. Okay.
You have about 5 minutes left.
Yeah. Next slide. And so here I have a kind of a very simple illustration cases. And we started a kind of 5-bus system. And then in the case number 2, we split the line somewhere in the middle in the two-thirds place. And using the dollar per megawatt formulation, the traditional formulation, another case 3 using the dollar per megawatt mile formulation. And then we also can split the line kind of like divided into multiple strands, and then look at the locational marginal price calculation result. Next slide. Oh, no, okay, I can skip this. This is just for background information. And this shows how, for example, if you want to play with this example, you can show this shows how exactly the objective term and the transmission constraint TDS formulation is being used. Okay. Next slide. And you can see that the case 1 and the total violation cost is $96,000. And on line 1 to 2, there is a 48 megawatt violation, right? But if we split it in case 2, if we split into that line into 2 sections, and using the traditional megawatt only based formulation, immediately the violation cost doubles. Okay? And because we have 2 separate constraints in the model. And both 2 separate both have to be relaxed by the same amount in order to generate a feasible solution. But in case number 3, and when the line, the penalty is weighted by the length of the line, and then we can see that it does not affect the result. The penalty cost is total penalty cost is $96,000. And similarly, when we kind of split the transmission line between bus 1 and bus 2 into 2 strands, and where the flows capacities are kind of halved, the impedance are doubled, and we still get the same result. So this will avoid all the unnecessary processing and provide a predictable result that's modeling choice invariant. Next. This is locational marginal price comparison between the different cases. Right? You can see that case 1, case 2, case 3, they all have the same locational marginal price at bus number 2. And for case 2, where the dollar megawatt method is used, it has a very high locational marginal price. Next slide. Conclusion. So we essentially based on some very intuitive fundamental engineering and economic principles. We proposed this megawatt mile based transmission demand curve remodeling approach to address the situation where you have used the transmission demand curve to resolve infeasibility issues because of transmission shortage, capacity shortage, and at the same time produce locational marginal price that's kind of predictable and are not subject to influence of arbitrary modeling choices. And this whole approach also, and this approach works quite well with the existing New York ISO's TDC by asset approach. So that's basically conclude the presentation.
All right, thank you very much. As a reminder, if you're attending online and have a question, please put it in the Q&A. Do we have any questions in the room?
Thank you for the presentation. It's very interesting. This is Zoe from DRW. I just have one quick question. Because in your model, you are trying to basically building this correlation, I mean, a formula based on the transmission capacity and also the line length, right?
Yes.
I'm just wondering because sometimes the binding constraint may show up in transformer as well. But for a transformer, how did you model this like length?
Oh, in that case, you do not. Then you do not. Transformer length is you can consider it as 0 or 1. You do not need to weight by the length. There is no the distance for transformer is not defined.
Have you tried?
So you just use say how much. Let's say you have a transformer 100 megawatt capacity, and then ask yourself how much would it cost to upgrade that capacity to transform car? Then you immediately have a number, right? So you don't need to scale by distance.
Have you considered other choice like using some like electrical distance, like reactance, something like that?
No, we have not. Yeah, this is purely based on very simple engineering economic principles. Say, if you have 2 line sections connected back to back, and how much does it cost to upgrade them, right? You cannot. Then the first is what capacity, right? Goes from capacity to 100 to 200, and over what distance? The distance, you generally, at least for AC transmission, is proportional to distance.
Can I say the biggest reason that you are choosing using this like a lens is because this kind of lens is the most costing factor in this like a planning upgrade?
Yeah.
Okay, I see. Thanks.
Yeah.
Do we have any questions online?
There is.
Yeah, thank you for the presentation. This is Bing Yan from Rochester Institute of Technology. Can you please go back to page 6, where you have the example like with 2 constraints? Anyway, we can go back to the presentation. Yeah, because we really need that figure. Yeah, great. Page 6. Yep, thank you. Yeah. So can you explain a little bit more about the figure? So you mean the feasible region is this like this green part, and now we have additional 2 constraints where will cause infeasibility, right?
That's right.
Yeah. And then one is C1 and one is C2. And if I enter correctly, so we first do this screening and we find out C1 and C2, they're redundant because they cause infeasibility at the same direction. Yeah. And now we solve the problem twice. So the first one is with area constraints with C1 and C2. And second one is solve the problem only with C2 because C2 has more impacts. Yeah, I think the reason why the kinetic condition mismatched is because like for the first problem, we do have this like a C1 and C2. There are soft constraints in the object function. So the impacts coming from the like evaluation of these 2 constraints, although they film the same direction. But then when we remove one of them, like we remove C1 and we solve a new problem, the object function is completely different. Because now we only have impact of the violation from C2.
Yeah.
Yeah, so I think that could be the reason why it's mismatch.
Yeah, actually, in some of the implementations, they do not actually remove them. They just effectively increase the limit so that it effectively neutralize it. So essentially, for example, they artificially change the limit to a new limit for constraint C1, and by adding the amount of violation to it. Okay. So that they think that the new solution will end up exactly the same place, but that it doesn't.
It doesn't.
It doesn't. Actually, it goes into the interior of the shaded region.
Yeah, right. Okay.
Yes.
Thank you.
You are absolutely correct.
Do we have any more questions? Do we have any more questions online? All right, then thank you very much. Okay, then we're wrapping up a little bit early, though we will see you all tomorrow at 9 8:30. We're just in one room tomorrow, so we'll be back at the commission meeting room, not in this room tomorrow. So have a good night. I'll see you all then. And thank you.
Thank you.